So, my dear students, I hope you all are having a great time. Student, once again, I welcome you all on this amazing platform of PhysicsWallah English channel. Student, in this ongoing champion series, now we have moved to lecture number 20, and in this particular lecture, we are going to discuss one of the most important chapter of organic chemistry, and that is alkyl and aryl halides. We also say it as halogen derivative. Students, if I talk about the content which we are going to discuss today, first we'll start with the introduction of alkyl and aryl halides. Introduction of alkyl and aryl halides. Then we'll talk about their classification of alkyl and aryl halides, right? Then we'll be talking about some important terminology related to organic chemistry. That's the introduction of electrophile, nucleophiles, living group, their living ability, solvent, carbocations, and their rearrangement. So some important terminology related to organic chemistry, right? Okay. Then we'll start with the general method of preparation of alkyl halides. GMP of alkyl halide. Then we'll be talking about the physical and chemical properties of alkyl and aryl halides. Physical properties first of all. Physical properties of alkyl halide. Then we'll talk about the chemical properties of alkyl halides, and here mainly we are going to discuss the two important chemical reactions which we have already discussed in that lecture, reaction mechanism. Once again we will redo it, that is nucleophilic substitution reaction and elimination reaction. So chemical reactions of alkyl halide, chemical reactions of alkyl halide. Here mainly we'll be discussing nucleophilic substitution reaction, that is SN reaction, and elimination reaction. If I further classify this SN reaction, it will be SN1, SN2, SNI, SNNGP, and in elimination reaction we'll be talking about E1, E2, and E1CB. Am I clear, students? And then we'll be talking about GMP of aryl halides, and at the last we'll be talking about chemical reactions of aryl halides, mainly SN-AE reaction and SN-EA reactions. Am I clear, students? So these are the things which we are going to discuss today. Although most of the thing we have discussed in the lecture number 3 itself, that was the lecture of reaction mechanism, but once again we will quickly touch all these things so that you can understand this chapter very easily. Friends, now let's start our discussion on the chapter alkyl and aryl halides. We also say it as halogen derivative. The reason is basically alkyl halides are the organic compounds derived from hydrocarbon by replacement of one or more hydrogen atoms by corresponding number of halogen atoms. Here simply from hydrocarbon, if I replace one or more hydrogen atom by corresponding number of halogen atom, the compound obtained is referred as alkyl or aryl halides. It may have the general formula Rx or may have the formula ARX, where AR is aryl, phenyl, ARX. It may have the general formula like this or may have the general formula like this. As you can see here, this is my alkyl part whereas this one is your halogen atom, right? Rx, or it may act as Ar or X. So basically they are simply the hydrocarbon where hydrogen atoms are replaced by halogen atom. The compound obtained is referred as alkyl or aryl halide. Now let's talk about the different types of alkyl and aryl halides. Student, now let's talk about the classification of alkyl and aryl halide. Student, on the basis of nature of hydrocarbon from which they are derived, halogen derivatives are classified as alkyl halides. If the halogen derivative is obtained from alkane family, so they will have a general formula CnH2n plus 1x, right? If the halogen derivative is obtained from alkene family, it is classified or it is referred as alkenyl halides. We'll have the general formula CnH2n minus 1x. If the halogen derivative is obtained from alkyne family, it is referred as alkynyl halides. We'll have a general formula CnH2n minus 3x. If the halogen derivative is obtained from aromatic hydrocarbon, then it is referred as aryl halides. We'll have the structural formula or the molecular formula PHX. Am I clear, students? Now, this alkyl halide is further classified as monohalide, dihalide, trihalide and tetrahalide depending on the number of halogen atoms attached to the alkyl chain. Am I clear? If one halogen atom, mono, two halogen atoms are connected to the alkyl chain, then it is di, 3 halogen atom, tri, 4 halogen atom, tetra. Am I clear? Now, student, this monohalide may be further classified as primary alkyl halides, secondary halides and tertiary halides. We'll talk about each and every alkyl halide in detail one by one. Student, first of all, let's talk about monohalides. The name itself says mono, single halogen atom, right? So here one hydrogen atom is replaced by one halogen atom, right? In alkane. So they will have a general formula CnH2n plus 1x. It is like this. Let's suppose I'm having propane. So from propane, what you need to do? You remove one hydrogen minus one H. What you are going to get? You are going to get propyl. C3H7. Now add one halogen atom, C3H7X. The compound obtained is propyl halide. So here one of the hydrogen atom is replaced by halogen atom. It's a monohalide. Am I clear, student? Second, dihalide. Two hydrogen atoms are replaced by two halogen atom in alkane molecule, right? If the two halogen atoms are connected to the same carbon, it is referred as geminal dihalide, like this, CXX. Both the halogen atoms are connected to the same carbon. It is geminal dihalide. Geminal dihalide. If the two halogen atoms are on adjacent carbon, it is referred as vicinal dihalide. Vicinal dihalide. Am I clear? Third one, trihalides. Here, 3 hydrogen atoms will be replaced by 3 halogen atoms. The best example is haloform CHX3. Am I clear, student? We can have chloroform CHCl3. It's an example of trihalide. Trihalide. It will have a general formula CnH2n minus 1x3. Am I clear? Let's move ahead. Tetrahalides. All the hydrogen atoms are replaced by halogen atom, or we say it as per halo compounds. They are obtained by the replacement of 4 hydrogen atoms by 4 halogen compounds. Am I clear? The best example is this CCl4, a non-polar solvent. Am I clear? Carbon tetrachloride, CCl4. It's a tetrahalide. Am I clear, student? Shall we move ahead? Okay. Student, now this monohalide may be further classified as primary alkyl halide, secondary halides, and tertiary halides depending on the nature of carbon to which this halogen atom is directly attached. Students, these are classified on the basis of nature of carbon atom carrying the halogen atom. Primary halides are 1 degree alkyl halide. If the halogen atom is directly connected to a 1 degree carbon like this, CCCCX. Student, if I talk about this particular compound, the halogen atom is connected to primary carbon. So it is referred as 1 degree alkyl halides or primary alkyl halide. Am I clear? Moving to the next one, secondary alkyl halide. Here, the halogen atom is connected to 2 degree carbon like this, CCCCCX. Student, if I talk about this halogen, it is connected to a secondary carbon because this carbon is connected to 2 carbons in the chain. Am I clear? So this particular carbon is a secondary carbon. Halogen attached to a secondary carbon is 2 degree alkyl halide. Am I clear? The next one, tertiary alkyl halides or 3 degree alkyl halide. Here, the halogen atom is directly connected to a 3 degree carbon like this. Am I clear? This particular carbon, it's a 3 degree carbon. Why it's a 3 degree carbon? Because this carbon is connected to how many carbon? 1, 2, 3 carbon in the chain. So it's a 3 degree carbon. Halogen connected to a 3 degree carbon, the compound obtained is referred as 3 degree alkyl halide, or we say it as tertiary alkyl halide. Am I clear, student? Okay. Let's talk about this particular thing. Okay. If halogen is connected to this one, this carbon is your 1 degree carbon, it will be referred as primary alkyl halide. If halogen is connected to this carbon, it will be referred as 3 degree alkyl halide because this carbon is a tertiary carbon connected to 3 carbons. If halogen is connected to this carbon, this carbon is a 2 degree carbon. So the alkyl halide obtained will be referred as secondary alkyl halide. If halogen is directly connected to this carbon, the alkyl halide will be referred as primary alkyl halide. Am I clear? Because these things are really important, and these things are the basics of this particular chapter, the fundamental things of this particular chapter. Students, now let's discuss some of the important terminology related to this particular chapter or related to entire organic chemistry. Okay, so let's first of all talk about solvent. Okay, student, basically we classify solvent into 2 different categories. The first one, polar, the second one, non-polar. If I talk about polar solvent, the dipole moment is non-zero, mu is not equals to 0. Whereas if I talk about non-polar solvent, mu equals to 0. Am I clear? The best example of non-polar solvent, CCl4, just now we have discussed. Normal hexane, benzene, all these are the examples of non-polar solvent. If I talk about polar solvent, the best example is water, alcohol, right? We have CH3, C double bond, O, CH3, acetone. So these are the examples of polar solvent. Here, dipole moment is non-zero. Now, this polar solvent is further classified in 2 categories, polar protic and polar aprotic solvent. We'll talk about it one by one. Students, now let's talk about polar protic solvent. The name itself says polar and then protic. So dipole moment has to be non-zero. The polar solvent which is having acidic hydrogen, protic stands for proton. proton is nothing but H plus, the solvent which is having acidic hydrogen, the solvent where one of the hydrogen atom is directly attached to a highly electronegative elements like nitrogen, oxygen or fluorine. Such solvents are referred as polar protic solvent. The best example, water, ROH, right? These are the examples of polar protic solvent. Student, if I talk about this polar protic solvent, they are having like water, HOH. If I talk about this water molecule, hydrogen will have delta positive, oxygen will have delta negative. Am I clear? So students, such solvent can solvate cations as well as anions. Polar protic solvent, let me write that. Polar protic solvent can solvate cations and anions, both, right? Because they are having del positive also, they are having a highly acidic hydrogen. At the same time, this electronegative element is also there, which is having a del negative charge. So they are the spherical species containing positive and negative charge. They can solvate both cations and anions. Am I clear? Let's move ahead. Student, if I talk about this polar aprotic solvent, the solvent whose dipole moment is non-zero, polar aprotic, which does not have a tendency to release H plus, where the hydrogen atom is not directly connected to a highly electronegative elements like nitrogen, oxygen and fluorine. Such solvents are polar aprotic solvent. The best example is ether, CH3OCH3. If I look at this particular molecule, it is having a certain dipole moment, so mu is not equals to 0. At the same time, these hydrogen atoms are connected to less electronegative element like carbon, so it is a polar aprotic solvent. The next one, acetone, CH3C double bond O CH3. Dipole moment is non-zero. At the same time, hydrogen is not connected to a highly electronegative element. Am I clear? Students, since they don't have any acidic hydrogen, they don't liberate H plus in the solution. Polar aprotic solvent mainly acts as a negatively charged spheres. So they have a tendency to solvate cations only. These polar aprotic solvents are used to solvate cations mainly. Am I clear? Whereas polar protic solvent can solvate cation as well as anion. Am I clear? Let's move ahead. Non-polar solvent. Already we have discussed it. Mu equals to 0. Example, CCl4. We have N-hexane, C6H14. N-hexane, benzene, all these are non-polar solvent. Some common examples of solvent: water, polar protic; ethanol, polar protic; acid, polar protic. All the acids where we have acidic hydrogen and where the dipole moment is non-zero, they are the examples of polar protic solvent. Ammonia, polar protic solvent. All these are polar protic solvent. Acetone, polar aprotic. Mu is not equals to 0, but it's here we don't have any acidic hydrogen, so it's a polar aprotic solvent. Next one, DMSO, dimethyl sulfoxide. Mu not equals to 0, so it's a polar solvent, but we don't have any acidic hydrogen, so it's a polar aprotic solvent. The next one, DMF, dimethyl formide. Once again, we don't have any acidic hydrogen. Hydrogen is attached to carbon, but the dipole moment is non-zero, so it's a polar aprotic solvent. DMA, once again, it's also a polar aprotic solvent. So DMSO, DMF, DMA, all these are polar aprotic solvent. They have a tendency to solvate cations, whereas water, alcohol, acetic acid, formic acids, ammonia, all these are the examples of polar protic solvent. Am I clear, students? Now let's move ahead. Friends, now let's start our discussion on some more important terminology related to this chapter, or we can say related to entire organic chemistry. And the first one is electrophile. Electro stands for electron and phile stands for lover, lover of electron. The species which is electron deficient may act as a lover of electron, right? So an electrophile is a positively charged species or neutral molecules with electron deficient center. And basically the electron deficient species are also referred as Lewis acids. So student, electrophiles are nothing but electron deficient species. They may be a cationic species, at the same time they may be a neutral molecule also, but with deficiency of electron. We'll discuss about the different types of electrophiles one by one. Positively charged electrophile. Student, in general, all the cationic species acts as electrophile. E plus, whenever you see any cationic species, simply put that in the category of electrophile. The electrophile is H plus, Br plus, Cl plus, I plus, NO2 plus, carbocations, NO plus. All these cationic species are electrophile, which you may see in organic chemistry. The next one, if I talk about neutral electrophiles, basically here the electrophiles which are neutral but has incomplete octet, such species are referred as neutral electrophiles, right? Like SO3, BF3, AlCl3, ZnCl2, all the Lewis acids whose octet is incomplete, such species are referred as neutral electrophiles, right? ZnCl2, FeCl3, RC double bond OCl, all these species are referred as neutral electrophile. Am I clear? So in these electrophiles, central atom has incomplete octet and at least one vacant orbital. Basically, we have studied it in the definition of Lewis acids. Either they have incomplete octet or they have a vacant p orbital or a vacant d orbital. Am I clear? Let's move ahead. Nucleo stands for nucleus and phile stands for lover. Lover of nucleus means lover of positively charged species. Which all species can act as a lover of positively charged species? All the electron rich species. So nucleophiles are nothing but electron rich species. Electron rich species. It may be an anionic species or maybe a neutral molecule containing at least one lone pair or maybe a neutral molecule containing loosely held pi bond. Am I clear? Okay, let's discuss it one by one. If I talk about negatively charged nucleophiles, all the anionic species are basically negatively charged nucleophiles like H minus, CS3 minus, or we can say R minus, NH2 minus, OH minus, right? All CN minus, SH minus, all these species are negatively charged nucleophiles. All the anions act as nucleophile. Am I clear? Next one, neutral molecules. In this nucleophile, central atom has complete octet and has at least one lone pair of electrons, right? Basically, the examples are ammonia, NH3, nitrogen, octet is complete, one lone pair, water molecule, oxygen atom, two lone pair, octet complete and two lone pair. This will act as a neutral nucleophile. Okay. We can have ROH alcohol acting as a neutral nucleophile. Students, even this CH2 doubly bond CH2 alkene, this one also act as a neutral nucleophile. Why? Because here the second bond is pi bond, and whenever this pi bond is formed, it is formed by the lateral overlap. Basically, it's loosely held pi electron, so it also act as a nucleophile. Benzene, this one also act as a nucleophilic center because it contains loosely held pi electron components. Loosely held pi electron components. Am I clear, students? Let's move ahead. I'm moving to the next type of nucleophiles which we have to study is there on the screen, and it is ambident nucleophile. Ambident nucleophiles, species having the two nucleophilic centers, but at a time donation will occur from only one center. The best example, cyanide ion. Student, here carbon is having a new negatively charged center, right? On this carbon we have a negative charge. At the same time nitrogen is having a lone pair. This carbon can also act as a nucleophilic center, and nitrogen can also act as a nucleophilic center, but at a time donation will occur from only one side. Such a nucleophile are referred as ambident nucleophile. Am I clear, students? Let's move ahead. Students, moving ahead, the next topic which we are going to discuss is there on the screen, and it's nothing but nucleophilicity and basicity. First of all, let's try to understand the term nucleophilicity. It is defined as the relative tendency of an electron-rich species to donate a pair of electron to electron-deficient center. The relative tendency of a nucleophile or an electron-rich species to donate a pair of electron to electron-deficient center is nothing but nucleophilicity, while basicity is defined as the relative tendency of an electron-rich species to snatch acidic hydrogen from any compound. The tendency of an atom to snatch acidic hydrogen from any compound is basicity, whereas the tendency of an electron-rich species to donate a pair of electron cloud to electron deficient center and form a sigma covalent bond with that electron deficient center is nothing but nucleophilicity. Let's try to understand this nucleophilicity and basicity in detail. Student, basically nucleophilicity is a kinetically controlled process. Let us try to understand what do we mean by the term kinetically controlled process. I'm having an electron deficient center A positive. This is my electron deficient center. Now I'm having two electron rich species, Y1 minus, Y2 minus. The electron rich species are referred as nucleophile. Now I am going to define nucleophilicity. Let's try to assume this Y1 minus is attacking on A plus and forming a sigma covalent bond with A, and the compound form is AY1. The time taken by this Y1 minus to attack on A plus, let's suppose it's 10 seconds. Now Y2 minus is also donating a pair of electron to this electron deficient center A plus and forming a sigma covalent bond AY2. The time taken by this Y2 minus to approach this A plus is 12 seconds. Which one is attacking at a faster rate? Y1 minus. So which one is a better nucleophile? Y1 minus. Am I clear? What do we mean by the term kinetically controlled process? Basically, nucleophilicity is all about kinetics. Here, speed matters the most. This Y1 minus is attacking at a faster rate, so it is a better nucleophile. Am I clear, student? Okay, students, now let's talk about basicity. How do we define it? Simply the relative tendency to snatch acidic hydrogen. The more is the tendency to snatch the acidic hydrogen, the better will be the basic strength. Am I clear, student? Okay, I'm having two electron rich species A minus and B minus. Both of them are treated with an acid HX having acidic hydrogen H plus, right? If this A minus is treated with HX, what it will do? It will snatch this H plus from HX and will form a compound HA. At the same time, X minus is also formed. Since the process is reversible, I am going to define equilibrium constant Ka1 for this, right? B minus, it will also have a tendency to snatch the acidic hydrogen and will form a covalent compound HB, right? And X minus is also released. For this, the equilibrium constant defined is Ka2. If Ka1 is greater than Ka2. What does it mean? It means at equilibrium, the concentration of Ha is more than that of Hb. Means the amount of Ha formed is more. And if amount of Ha formed is more, means maximum amount of this H plus has been snatched from this acid. And basicity is nothing but the relative ability to snatch H plus. Can I say, student, this basicity is a thermodynamically controlled process because it's dependent on Ka and Kb values. Am I clear? More is the tendency to snatch the acidic hydrogen, better is the basic strength. Faster is the ability to form a sigma covalent bond with electron deficient center, better is the nucleophilic strength. Am I clear? Shall we move ahead? Let's move ahead. Students, now let's talk about the factors which affect nucleophilicity as well as basic strength. First of all, if I talk about nucleophilicity or even basic strength, a anionic species is a better base as well as a better nucleophile as compared to a neutral molecule like OH minus and H2O. Which one is a better base? OH minus. Which one is a better nucleophile? OH minus. SH minus and H2S. Which one is a better base? SH minus. Which one is a better nucleophile? SH minus. Am I clear? Anionic species or negatively charged species is a better base as well as a better nucleophile as compared to a neutral one. NH2 negative is a better nucleophile as compared to NH3. Am I clear? I hope this parameter is clear. The next one. If donor atom is same, higher the electron density, better will be the basic strength as well as in most cases better will be the nucleophilic strength also. If the donor atom is same, higher the electron density, higher will be the basic strength. Higher will be the basic strength. Let's try to understand this one with one example. I'm having OH minus and I'm having RO minus. Donation is occurring from oxygen atom. Donor atom is same. Now in case of RO minus, this alkyl will act as a plus I group. It will increase the electron density on oxygen. More is the charge density, better will be the basic strength, and in most cases better will be the nucleophilic strength also. Am I clear? If I have to compare the nucleophilicity of CH3O minus and OH minus, this CH3O minus is a better nucleophile as well as a better base. Am I clear, student? Let's move ahead. And now let's discuss the effect of solvent on nucleophilicity as well as basicity. Student, we have two types of solvent: polar solvent, non-polar solvent. Further, this polar solvent is divided in two categories: polar protic, polar aprotic. Polar protic solvent can solvate cation as well as anion, right? And the extent of solvation depends on charge density. Higher is the charge density, more is the extent of solvation, right, student? And now, in which case the charge density will be more? Smaller the size of ion, more is the charge density, right? So can I say, if I talk about this F minus, Cl minus, Br minus, I minus, where the charge density will be more? Charge density will be maximum in case of fluoride ion. Now, extent of solvation depends on charge density. So which one will be solvated to a maximum extent? F minus. More is the solvation, lesser is the nucleophilic strength. Am I clear? So student, in case of polar protic solvent, larger the size of anion, better is the nucleophilic strength. So in case of polar protic solvent, I minus is a better nucleophile, then Br minus, then Cl minus, then F minus, because the solvation of I minus is less. More the solvation, lesser is the nucleophilic strength. Am I clear, student? Okay. If I talk about basic strength does not depend on it. Basic strength simply depends on charge density. Higher is the charge density, better is the basic strength. So which one will be a better base? F minus or I minus? F minus is a better base. Which one is a better nucleophile in case of polar protic solvent? I minus is a better nucleophile. Am I clear? Now, if I talk about polar aprotic solvent like DMSO, already I have told you this polar aprotic solvent acts as a negatively charged spheres. So they cannot solvate anion, right? They will not touch anion. In this case, nucleophilicity as well as basic strength will simply depend on charge density. Higher the charge density, more is the nucleophilicity as well as basic strength. So in case of aprotic solvent or polar aprotic solvent, F minus is a better nucleophile, then Cl minus, then Br minus, then I minus. I hope these things are crystal clear to you all. Shall we move ahead? Let's move ahead. Students, the next factor which we are going to discuss is steric effect on nucleophilicity. Student, we have already discussed this nucleophilicity is a kinetically controlled process, right? Now, if the size is more, obviously the mobility will be less, the nucleophilicity will be less. So with increase in the steric crowding, nucleophilicity decreases if the donor atom is same. Am I clear? While basic strength has nothing to do with speed, it simply depends on charge density. So if I take this example, CS3 O minus and this one terbutoxide CCCO minus. In both the case, donor atom is oxygen. Now, in which case do you say steric crowding is more? In case of terbutoxide ion, TBuO minus. This is terbutoxide ion. In case of terbutoxide ion, steric crowding is more, mobility will be less, so nucleophilic strength will be less. So which one is a better nucleophile? CS3O minus is a better nucleophile. Now if I talk about basic strength, which one is a better base? Basic strength simply depends on charge density. This terbutoxide ion is a better base. Am I clear, student? I hope this particular factor is also crystal clear. Let's move ahead. Periodicity. Student, both nucleophilicity as well as basic strength decreases as we move from left to right across a period. Let's talk about it. I'm having CS3 minus, NH2 minus, OH minus, F minus. Student, across a period, size almost remains the same. There is not much significance in change in atomic size. Now here, nucleophilicity as well as basic strength will depend on electronegativity. F minus, more electronegative, will have a lesser tendency to donate. Lesser is the donation ability, lesser will be the nucleophilicity, as well as lesser will be the basic strength. C, being less electronegative, will have a more donation ability. More is the donation ability, better will be the nucleophilicity, better will be the basic strength. So both nucleophilicity as well as basic strength decreases as we move from left to right across a period. Across a period, nucleophilicity as well as basic strength decreases. Is this clear? Shall we move ahead? Let's move ahead. Student, these are some of the examples through which we can understand nucleophilicity and basicity. Across a period, both nucleophilicity as well as basicity decreases if we move from left to right. Am I clear? Okay. Next one. SiS3PS same. Third period elements, right? As I move from in third period from left to right, the electronegativity will increase. With increase in electronegativity, donation ability will decrease. Nucleophilicity as well as basic strength will decrease. Next one, F minus, Cl minus, Br minus, I minus. If I talk about nucleophilicity, I minus is a better nucleophile in polar protic solvent, whereas in any solvent, F minus is a better base. So this is the basic strength order, whereas this one is the nucleophilic strength order in polar protic solvent. Am I clear, student? Now, one more important point. OH minus and SH minus, which one is a better nucleophile? SH minus is a better nucleophile as compared to OH minus. Why? Because this OH minus will get solvated, right? More is the extent of solvation, lesser is the nucleophilicity. SH minus will be solvated to a lesser extent as compared to OH minus. So which one is a better nucleophile? SH minus. But basic strength depends on charge density. OH minus will have higher charge density. So OH minus will be a better base as compared to SH minus. Am I clear, students? Next. Same story here also. O minus, S minus. Student, if I talk about nucleophilicity in polar protic solvent, larger the size of anion, lesser is the solvation, better is the nucleophilic strength. Whereas basic strength simply depends on charge density. O minus will have higher charge density as compared to S minus. So RO minus is a better base as compared to RS minus. I hope these things are crystal clear to you all. I hope this nucleophilicity, basicity, nucleophile, base, all these things are clear to you all now, right? So shall we move ahead? Let's move ahead. The next thing that we are going to discuss is there on the screen, and it's living ability of a living group. Let's try to understand it. Student, in most of the substitution reaction or elimination reaction, one of the group has to depart, right? And that particular group is referred as living group. Now the living ability of a living group simply depends on the stability of this Lg minus, because after departure it will get converted into anionic state most of the time. Now if this ion Lg minus is more stable, the living ability will be much better. Am I clear? Higher is the stability of Lg minus, higher is the stability of Lg minus, better will be the living ability. One more point. Student, if this Lg minus is more stable, can I say it will have a less tendency to react, right? It will have less donation ability. In that case, if it is having a less donation ability, can I say it will be relatively a weaker base? So student, basically good living group are a weaker base. If I have to compare the living ability of a living group, simply compare the basic strength. If it is a poor base, it will be a good living group. Let's try to understand it with one example. I'm having F minus, Cl minus, Br minus, I minus. What do you say? Which one is more stable? I minus being more stable, charge density less, lesser the charge density, more is the stability of ion. Now if it is more stable, it will have less donation ability. So I minus is a weaker base, and if it is a weaker base, it is a good living group. Am I clear? It will have more tendency to leave the substrate as compared to fluoride ion, as compared to chloride ion, bromide ion. Am I clear? Higher is the stability of ion after departure, better is the leaving ability. Or I can simply say leaving ability is inversely proportional to basic strength, right? Student, now let's discuss the living order of some of the important compounds. If I have to talk about this one, F minus, Cl minus, Br minus, I minus, which one is a better living group? I minus is a better living group as compared to Br minus. This Br minus is a better living group as compared to Cl minus. And Cl minus is a better living group as compared to chloride ion. OH minus, SH minus, which one is a better living group? Charge density on SH minus is less. Lesser the charge density, better is the living ability. SH minus will be a better living group as compared to OH minus. Am I clear? Student, we have some of the best living group like N2 positive, H2O positive, H2S positive. Then we have tosylate ion, right? Tosylate ion is like this. S double bond O, O minus, CS3. We have nitrosylate ion, we have brosylate ion. All these groups are very good living groups. Even triflate ion, CFF, S double bond O, O minus. These are some of the very good living group. If you want to study about this living ability, the living order in more detail, please refer to lecture number 3. That's the lecture of reaction mechanism. There I have thoroughly discussed the basic strength, the nucleophilicity, nucleophile, living ability, the living groups, all these things I have discussed thoroughly. So if you want to study in detail, please refer to lecture number 3. Students, now it's time to discuss the GMP of alkyl halides. Students, now let's discuss the different methods through which we can synthesize alkyl halide. Student, alkyl halide can be synthesized from n number of organic compounds. Starting with hydrocarbon, even it can be synthesized from alkane also. In hydrocarbon, we have studied a very important chemical reactions of alkane, and that was photohalogenation, right? Whenever alkane is treated with halogen in the presence of photon, we have free radical substitution reaction occurring, and the product formed is alkyl halide. Student, so I'm having my alkane RH. It's treated with halogen in the presence of photon H nu. The product which we get is RX, alkyl halide. The reaction occurs via free radical pathway. This reaction is referred as free radical substitution reaction, right? We have studied about this reaction, the entire mechanism, all these things. If you have any doubt, please refer to the lecture of hydrocarbon. Student, here basically the reaction occurs in 3 different steps: initiation step, chain propagation step, and then termination step. Am I clear? The rate of reaction depends on the stability of free radical, the alkyl free radical R dot. More is the stability of R dot, faster will be the rate of this reaction, and faster will be the rate of formation of alkyl halides. Am I clear? So, rate of reaction depends on the stability of R dot, since R dot is formed as RDS. Am I clear? Student, here the rate of formation of alkyl halide also depends on the reactivity of X dot. Am I clear? In the first step itself, in the chain initiation step itself, this X dot is formed. So the rate of formation of alkyl halide from alkane depends on the stability of R dot. A 3-degree alkyl radical is more stable as compared to 2-degree, more stable as compared to 1-degree. Am I clear? At the same time, it also depends on the reactivity of halide radical or halogen radical, and here this F dot is more reactive as compared to Cl dot, Br dot, and I dot is very less reactive. Student, in general this fluorination is avoided because this reaction is a very violent reaction. Am I clear? We have just discussed each and every point related to this free radical substitution reaction in the chapter hydrocarbon, right? Students, moving ahead, we can synthesize alkyl halide even from alkene. If we treat alkene with HX, that is halic acid, in that case also we can get alkyl halide. Student, basically here the reaction occurs in two different pathways. One of the pathways referred as Markovnikov and the other one is anti-Markovnikov. We have discussed all these things. Let's quickly revise that. Student, if this HX is any acid like HCl, HBr, HI, in that case, and if it's treated in dark, or if even its dark is not mentioned, simply you treat alkene with any of these acids, HCl, HBr, HI. First step is the protonation of alkene. As soon as this alkene is protonated, I will have the formation of carbocation. As soon as this carbocation is formed, it will undergo rearrangement to give us a more stable carbocation, and to this more stable carbocation this X minus will attack, right? And I will have my product as Markovnikov product, and the product formed is alkyl halides. So alkene treated with HCl, HBr, HI in dark, or even if dark is not mentioned, will give us Markovnikov product, and the product is alkyl halide. Alkene treated with HBr in the presence of R2O2, in the presence of H2O2, even in the presence of H nu photons. Here I will have anti-Markovnikov product. This halide ion will get substituted to the less crowded carbon, to the less substituted carbon. Am I clear, students? So alkene on treatment with HX leads to the formation of alkyl halide. Depending on the nature of reaction, we may have Markovnikov product, we may have anti-Markovnikov product. Student, there is one more way through which we can synthesize alkyl halides. Students, there is one more way through which we can synthesize alkyl halides. And in this particular case, we are going to get vicinal dihalide system. We have studied this reaction also, which is there on your screen. Alkene treated with halogen in the presence of non-polar solvent gives us the formation of a vicinal dihalide system. Both the halogen will be at anti-position with respect to each other, stereo-wise. Am I clear? First, we'll have the formation of a 3-member cyclic ring or cyclic halonium ion, and then the nucleophilic part X minus will approach from the back side, and I will have the formation of vicinal dihalide system. Both the halogens at anti with respect to each other. This particular reaction is referred as electrophilic addition reaction of alkene. We have studied it, right? We can synthesize dihalide through this. We can synthesize alkyl halide even from alkynes. The third hydrocarbon, alkyne. From alkyne, let's suppose this is one of the substrate. This is alkyne. It's treated with 2 equivalents of 2 moles of HX. Student, what will happen in the first step? First, this alkyne will react with 1 equivalent of HX. It will undergo electrophilic addition reaction, and I will have the formation of a vinylic halide system like this. Vinylic halide. Now it's further treated with HX. Now you may say, where we are going to form the carbocation? You may say, sir, here. Let's form the carbocation here, because here halogen is attached, and this halogen is a electronegative element, so it will destabilize. No. Student, although this halogen is an electronegative element, still it is having a lone pair. So it will stabilize the carbocation form via resonance. And the carbocation stabilized by resonance is a highly stable carbocation, right? Okay. So I am going to form carbocation here only. On this carbocation, this halide ion will further attack, and I will have the formation of geminal dihalide. Geminal dihalide. So if alkyne is treated with two equivalents of HX, in that case we will get geminal dihalide. First I will have the formation of vicinal halide. First I will have the formation of vinylic halide. Vinylic halide. This vinylic halide will further react with HX and will lead to the formation of geminal dihalide. Student, this is how we synthesize alkyl halides from different hydrocarbons, from alkene via free radical substitution reaction, from alkene via mainly electrophilic addition reaction, from alkyne via electrophilic addition reaction. Am I clear? Student, even we can synthesize this alkyl halide from alcohol, and most of the time we do this reaction only. Friends, moving ahead, the next method through which we can synthesize alkyl halide is from alcohol by nucleophilic substitution reaction. Although we have n number of methods through which we can synthesize alkyl halide from alcohol, we'll discuss all these methods one by one. Student, if alcohol is treated with HX, it will lead to the formation of alkyl halide, but there is certain condition. First, this HX is generally either HBr or HI, because these are a stronger acid and it can readily protonate alcohol. Am I clear? This HX should not be HF, because HF does not readily protonate alcohol. If this HX is HCl, then we have studied it, Lucas test, right? In the chapter alcohol, HCl is taken with ZnCl2, right? HCl taken with ZnCl2. If alcohol is treated with HCl in the presence of ZnCl2, in that case we get RCl, turbidity, right? And depending on the nature of substrate, the timing for this reaction is different. We get instant turbidity if this alcohol is 3 degree. We get turbidity after 5 to 10 minutes if it is a 2 degree alcohol, and if it's a 1 degree alcohol or methyl alcohol, in this case we get turbidity after prolonged heating. Student, if I talk about the mechanism of this reaction, first this HX acts as a source of H plus, and this H plus will protonate alcohol. ROH H plus, protonation of alcohol, ROH H positive. This H2O positive will act as a very good leaving group, and it will have a tendency to get departed as soon as this X minus attacks on this R part. As soon as it attacks here, this one gets departed, and I will have the formation of RX, which is nothing but alkyl halide. Am I clear? I hope this particular method is also clear to you all. Let's move ahead. There are few more methods through which we can generate alkyl halides from alcohol. If we treat alcohol with any chlorinating reagent like PCl3, PCl5, SOCl2, SOCl2 in the presence of the base pyridine, we are going to get alkyl halide. Let's discuss each of these reactions one by one. If alcohol ROH is treated with PCl3, here student, 1 mole of PCl3 is treated with 3 moles of alcohol, and the product which we get is RCl, 3 moles of alkyl chloride, plus the second byproduct or the byproduct which we get is H3PO3. Alcohol treated with PCl3, The product obtained is RCl. Student, here the reaction occurs via SN2 pathway. We have discussed this SN2 pathway in this lecture only. It's a nucleophilic substitution reaction. We have discussed this particular reaction pathway in this lecture only while discussing chemical properties. Okay. So we will have a inverted product. If I talk about the stereo, here we get a inverted product. Inverted product. Am I clear? Next one. Alcohol treated with PCl5. Student, in this case also the reaction occurs via SN2 pathway. The product obtained is alkyl chloride once again, and here the byproduct is POCl3. POCl3. Am I clear? Alcohol treated with PCl3 gives us RCl plus H3PO3, whereas alcohol treated with PCl5 gives us alkyl chloride, that is RCl plus P double bond O Cl3. Am I clear? Next one. Alcohol treated with SOCl2. Here the reaction occurs via SNI pathway. Here the reaction occurs via SNI pathway, intramolecular nucleophilic substitution reaction. The product which we get once again is alkyl chloride. Here, if I talk about the stereo of this particular reaction, retention occur. Retention in configuration. In configuration. Am I clear? And the second product is SO2 plus HCl. That's not more important. Student, this is one of the most widely used method for the preparation of alkyl halide from alcohol. Am I clear? We have one more method through which we can synthesize alkyl halide from alcohol. That's once again via SOCl2 only. ROH, alcohol treated with SOCl2 in the presence of base. That the base taken is pyridine. Here, student, the product which we get is alkyl chloride only, but here the reaction occurs via SN2 pathway. The byproduct is SO2 plus HCl. Am I clear? So these are the different reagents. With the help of these reagents, we can synthesize alkyl halides from alcohol. Alcohol treated with PCl5, PCl3, SOCl2. In all these cases, the product which we get is alkyl chloride. Alkyl chloride. Am I clear? Let's move ahead. Students, we can synthesize alkyl halide even from ethers. Ethers, whenever treated with HI, leads to the formation of alkyl iodide. We have studied this particular reaction in the chapter alcohol phenol ether. That was one of the most important reaction of ether. Reaction of ethers with HI. Let's quickly revise that. Ethers. From ether, synthesis of alkyl iodide. I'm having ROR dash, one unsymmetrical ether, and this unsymmetrical ether is treated with HI. I will have the formation of ROH plus R dash I. We have studied the mechanism of this reaction earlier only, so there is no need to discuss the same mechanism once again. Am I clear, student? If you have any doubt, please refer to the lecture of alcohol phenol ether. Let's take one example. I'm having anisole PHOCH3. This is my unsymmetrical ether. And now it's treated with HI, concentrated. What will be the product? This HI will act as a source of H+. It will protonate the oxygen. So I will have the formation of phenol. Apart from phenol, I will have my product CH3I. It's nothing but alkyl halide. Student, we can even synthesize alkyl halides if we treat ether with chlorinating reagent like PCl3 or PCl5. If I treat ether with PCl3, in that case also we are going to get alkyl halides. Am I clear, student? Now let's move to the next method. Moving to the next method through which we can synthesize alkyl halide is from carboxylic acid. Here, first we treat carboxylic acid RC double bond O OH with moist Ag2O. Moist Ag2O. This moist Ag2O, here I will have acid base reaction and it will lead to the formation of RC double bond O minus Ag plus, silver salt of carboxylic acid. This silver salt of carboxylic acid RC double bond O minus Ag plus is treated with Br2 in the presence of a non-polar solvent CCl4. Student, here this CO2 will get eliminated. Br2, from here I will generate Br dot. From here I will generate R dot. This R dot and Br dot will do combination reaction and I will have the formation of RBr plus CO2 plus AgBr will get precipitated. Am I clear, student? So whenever silver salt of carboxylic acid is treated with bromine in the presence of non-polar solvent, we will have the formation of alkyl halide with one lesser carbon atom, because one of the carbon atom is getting removed in the form of CO2 gas. I hope this particular reaction is also crystal clear to you all. Let's move ahead. Friends, moving ahead, now let's discuss these two questions related to Hunt's-Dicker reaction. Okay, student, if I talk about the first one, I am given acetic acid and I need to convert this acetic acid to CH3Br using a series of reagents. Can you convert it? Please try it. I'm having acetic acid CH3C double bond OOH. One of the method is through Hunt's-Dicker. Treat it with Ag2O, form CH3, C double bond O minus Ag plus silver salt of acid, right? And then treat it with Br2 in the presence of CCl4. You are going to get CH3Br. This is one of the method through which we can convert acetic acid to CH3Br. We have one more method through which we can do this conversion. I'm given same acetic acid CH3 C double bond OOH. Can I use soda lime? What the soda lime will do? Decarboxylation reaction. NaOH plus CaO. And this soda lime will do decarboxylation and I will have the formation of methane gas. Now this methane will be treated with Br2, right? Photohalogenation of methane will give me CH3Br. Am I clear, student? Here this alkyl or this methane should be taken in excess, because if bromine is taken in excess, then further I will have dihalogenation, trihalogenation, and like that. Am I clear? We have studied all these things in the chapter hydrocarbon. We have one more compound, that is toluene, and I need to convert this toluene to bromobenzene. Can you do this particular conversion? Let's try. I'm having PHCH3. CH3. If I use KMNO4, hot KMNO4, I'm having benzylic hydrogen. This benzylic hydrogen treated with KMNO4, I will have the formation of benzoic acid, OH. Am I clear? Use soda lime, NaOH plus CaO. You are going to get benzene, right? Now treat this benzene with Br2 in the presence of Fe. You are going to get bromobenzene. One more method is there. As soon as you are having this benzoic acid, treat it with Ag2O, you are going to get silver salt of acid, and then treat it with Br2. In the presence of CCl4, you are going to get bromobenzene. Am I clear? Let's move ahead. Student, moving ahead, the next method of preparation which we have to study for the formation of alkyl halide is a very important reaction, and this particular reaction is a halogen exchange reaction. Already I am having alkyl halide. Any alkyl halide, we can have alkyl chloride or alkyl bromide, and then if I want alkyl iodide, I am going to use this particular reaction. Conversion of any alkyl halide, mainly alkyl chloride, that is RCl or RBr, to alkyl iodide. This particular method is used, and the reaction is Finkelstein reaction. What happens here? I'm having any alkyl halide RX. This RX is treated with NaI in the presence of polar aprotic solvent acetone. Student, here we observe halogen exchange reaction. This NaI is a source of I minus, and it will do substitution reaction, and I will have the formation of alkyl iodide plus I will have the precipitation of NaX, PPT. Am I clear? This NaX is not soluble in the solvent acetone. Let's take one example. Suppose I'm having CH3, CH2, CH2Cl, and now it is treated with NaI and acetone. Why I am taking acetone? Because this NaI is soluble in acetone, whereas the compound NaX will be insoluble. Let's see here. As soon as this CH3, CH2, CH2Cl is treated with NaI, this NaI is a source of I minus. It will do substitution reaction, and I will have the formation of CH3, CH2, CH2I plus NaCl. Now, this NaI is soluble in acetone. As soon as it is soluble in acetone, it will act as a source of I minus. But this NaCl is insoluble, so I will have the formation of precipitate of this NaCl. And student, precipitation reaction is irreversible reaction, so the reaction will progress in this particular direction easily. Am I clear? So Finkelstein reaction is a halogen exchange reaction used for the preparation of alkyl iodide. Here we take substrate as alkyl chloride or alkyl bromide. This alkyl chloride or alkyl bromide, whenever treated with NaI in the presence of acetone, gives us alkyl iodide. Along with alkyl iodide, we may get a precipitate of NaX, because this NaCl, NaBr is having less covalent character, right? It is having more ionic character, and ionic compounds are less soluble in polar aprotic solvent, right? Whereas this NaI is having more covalent character. Larger the size of anion, more is the covalent character. That's why this NaI is more soluble in acetone, and if it is soluble in acetone, it will act as a source of I minus. Am I clear, students? So this is how Finkelstein reaction occurs, and it gives us alkyl iodide. It's an example of halogen exchange reaction. One of the halogen is exchanged by iodide ion. This X can either be Cl or Br. Am I clear? Let's move ahead. Student, we have one more example of halogen exchange reaction, and it's Schwarz reaction. Schwarz reaction. It's mainly used for the formation of, or exclusively used for the formation of alkyl fluoride. Alkyl fluoride. Am I clear? I may have any alkyl halide, that is Rx. It can be RCl, RBr, anything. RCl. Now it is treated with AgF. The reagents which you can use is either AgF, Hg2F2, right? You can use COF2, anything. Okay. As soon as this alkyl halide is treated with either AgF, either Hg2F2, I will have halogen exchange reaction. This AgF will act as a source of F minus. It will do substitution reaction. I will have the formation of alkyl fluoride. Along with this, we will get a precipitate of AgX. Since here chloride is there, so I will have the precipitation of AgCl. Am I clear? So this Schwartz reaction is primarily used for the preparation of alkyl fluoride. We can take any alkyl halide as a substrate. The reagent taken is either AgF, Hg2F2 or SbF3. In all case, we are going to get alkyl fluoride along with the precipitation of either AgX, Hg2X2 or SbX3. Students, now let's discuss the chemical properties and the chemical reactions of alkyl halide. Now let's discuss the chemical properties and the chemical reactions of alkyl halide. If we look at the structure of alkyl halide, here halogen is directly attached to carbon atom. Between carbon and halogen, which one is more electronegative? Halogen. If it is more electronegative, because of inductive effect, can I say all the sigma electron clouds will be shifted towards halogen atom? Will be shifted towards halogen atom. And if the electron clouds will be shifted towards halogen atom, can I say on halogen I will have a del negative charge, whereas on the carbon part I will have a del positive charge. Am I clear, student? So since halogen atoms are more electronegative than the carbon atom, the carbon halogen bonds of alkyl halide is polarized. If I talk about the chemical reactions of alkyl halide, it mainly shows two types of reaction. One, nucleophilic substitution reaction, Rx treated with a nucleophile Nu minus. The reaction is referred as nucleophilic substitution reaction. It also shows one more important reaction where an alkyl halide is treated with a base B minus, and here we will have elimination reaction. Elimination reaction. So these are the two most important reactions of alkyl halide. The first one is nucleophilic substitution reaction, where an alkyl halide is treated with a nucleophile, and there we will have a substitution reaction. And the second one is elimination reaction, where the alkyl halide is treated with a base and the product which we get is in general alkene. We'll discuss it one by one. Let's start with nucleophilic substitution reaction itself. Student, if I talk about this nucleophilic substitution reaction, I'm having my substrate alkyl halide. Now this alkyl halide is treated with a nucleophile Nu minus, right? And the product which we get is RNO, right? So simply a nucleophile is substituting this halogen atom and the product is RNO. Now student, we can have different pathway through which this reaction can occur. So basically nucleophilic substitution reaction can be classified as SN1 reaction, SN2 reaction, SN-NGP and SNI reactions. Depending on the nature of substrate, depending on the nature of nucleophile, we can have different types of nucleophilic substitution reaction. All these reaction mechanism, reactions pathway we have discussed in the third lecture. Here we will briefly discuss about all these parts: SN1, SN2, SN-NGP as well as SNI. Let's start one by one. Let's first of all talk about SN1 reaction. The name itself says SN1. SN stands for nucleophilic substitution, 1 unimolecular substitution reaction. Student, basically if I talk about this particular reaction, I'm having my substrate alkyl halide. This alkyl halide is treated with a polar protic solvent. In the presence of this polar protic solvent, first the substrate will get ionized. Ionization of substrate will occur, and can I say here basically with the ionization this halogen will depart and I will have the formation of carbocation. Student, whenever a carbocation is formed, it readily undergo rearrangement if there is a possibility of rearrangement. So this carbocation will undergo rearrangement to form the most stable carbocation. Now I am having my most stable carbocation R+. On this most stable carbocation, the nucleophile will attack. And student, if I talk about the structure of this carbocation, what's the hybridization? sp2. And if it is sp2 hybridized, can I say it will have a planar geometry? Right? And if the molecule is planar, so nucleophile can approach from front side as well as from the back side. So how many products are possible? 2 products. And can I say both these products will be mirror image of each other? So students, the product which we may get is RNU plus NUR. If the product formed is chiral, in that case we will have a racemic mixture. If the product which we are getting is a chiral, if it's optically active, then there will be the mirror image of each other, and in that case we will have racemization. Am I clear, students? This is how SN1 reaction occur. Unimolecular reaction, basically it occurs in 2 steps. First step is the ionization step. Step 1, ionization, which is initiated by a polar protic solvent. In general, protic solvent. This solvent ionizes the substrate, ionizes alkyl halide, and I will have the formation of carbocation. Second step is the first step, attack of nucleophile. Attack of nucleophile. Student, now if it's a 2-step process, can I say it's a complex reaction, right? Now it's a 2-step process. Can you say which step is a faster step? The faster step is the attack of nucleophile. So which one is the slower step? Formation of carbocation. Whenever a carbocation is formed, the formation of carbocation always occurs in slow step. Why? Because a neutral molecule Rx is getting converted to a charged species, R positive. Right? So this step is relatively a slower step, and slower step is the rate determining step. Is the first step involving nucleophile? No, the first step does not involve nucleophile. So can I say SN1 reaction is independent of nucleophile? It is independent on the nature of nucleophile. It has nothing to do with the nucleophilicity of nucleophile, as well as it is independent of concentration of nucleophile. Am I clear, student? It simply depends on my substrate. We'll talk about it. So student, can I say the rate of reaction will simply depend on the concentration of alkyl halide. It will be independent of the concentration of nucleophile. Independent of concentration of nucleophile, independent on nature of nucleophile. Am I clear? Shall I move ahead? Okay. Carbocation intermediate is formed, so rearrangement is possible. Rate of reaction is directly proportional to concentration of alkyl halide, or can I say rate of reaction is some constant, rate constant into alkyl halide to the power 1. Unimolecular reaction. Molecularity of this reaction is 1, order of reaction is 1, independent of nucleophile. Let's move ahead. Student, if I talk about the potential energy versus reaction progress of this SN1 reaction, it's like this. First, I'm having my substrate treated with a nucleophile. This is alkyl halide. Alkyl halide. It's treated with a nucleophile Nu-. Student, in the first step, this alkyl halide simply gets ionized in the presence of polar protic solvent, mainly H2O, ROH, any protic solvent. Since the reaction is initiated by a solvent, SN1 reaction is also referred as solvolysis reaction. Solvolysis reaction. Am I clear? Initiated by a solvent, that's why SN1 reaction referred as solvolysis. Now, with the help of solvent, I will have my first transition state where my leaving group, that is halide ion, is about to depart. I will have R X. On X, I will have del negative. On R, I will have del positive. Now we get the intermediate when this departure of halide ion has occurred, and I will have the formation of carbocation R+. As soon as this carbocation is formed, it is obtained as an intermediate. Intermediate. Now it may undergo rearrangement to give us a more stable carbocation. Finally, on the most stable carbocation, the nucleophile will approach from the front side as well as it may approach from the back side because it's planar in nature, right? The geometry is sp2. Geometry is planar. Hybridization is sp2. Am I clear, student? Okay. So this is my second TS where the nucleophile is partially getting connected to the alkyl part, and finally my product is RNU plus X minus. This is the free energy versus progress of reaction for SN1 reaction. Shall we move ahead? Let's move ahead. Student, if I talk about the stereochemistry of this SN1 reaction, we get carbocation C plus or we get R plus. This R plus is having a vacant p orbital, right? I will have a geometry like this, R. So the nucleophile may approach from the front side as well as the nucleophile may approach from the back side. So in case of SN1 reaction, we get enantiomeric product if the product obtained is optically active, and we will have racemic mixture. Racemic mixture obtained. Now, the extent of racemization will depend on the stability of carbocation. More is the stability of carbocation, higher will be the extent of racemization. Am I clear? Shall I move ahead? Let's move ahead. Students, now it's time to discuss the factors affecting SN1 reaction. This is really important. Student, if we look at the mechanism of this SN1 reaction, the first step is the ionization step. Alkyl halide treated with PPS, polar protic solvent, and we will have the formation of carbocation. Can I say more is the stability of this carbocation, better will be the rate of reaction? Higher the stability of carbocation, lesser will be the activation energy barrier, faster will be the rate of reaction. Am I clear, student? So can I say a 3-degree alkyl halide will give me a more stable carbocation as compared to a 2-degree alkyl halide, and 2-degree alkyl halide will give me a more stable carbocation as compared to 1-degree alkyl halide. So can I say rate of SN1 reaction, if I have to compare rate of SN1, maximum 3-degree alkyl halide. Why? Because in 3-degree alkyl halide, I will have a 3-degree carbocation, which is much more stable because of hyperconjugation. Then I will have 2-degree alkyl halide. In 1-degree alkyl halide generally, or primary alkyl halide, SN1 reaction does not occur readily. SN1 reaction mainly occurs in 3-degree alkyl halide or 2-degree alkyl halide or resonance stabilized alkyl halide, or where we have a resonance stabilized carbocation. like allylic halides, benzylic halides. In such cases also, this SN1 reaction will occur at a faster rate. Am I clear, student? Now let's see some alkyl halide, and we have to check whether SN1 reaction will occur or not, or if it's occurring, whether it will occur at a faster rate or at a slower rate. Okay. If I talk about such type of halides, no doubt this particular carbon is a 3-degree carbon, so it's a 3-degree alkyl halide. And some of you may say, so it will give a more stable carbocation. Student, it will not give SN1 reaction. No SN1. Can you tell me the reason? Student, as soon as this halogen is getting departed, I will have a bridgehead carbocation, and bridgehead carbocation formation is not visible. A bridgehead carbon cannot be planar in accordance with Brett's rule. Am I clear? So it will not give SN1 reaction. This one, CH2 doubly bonded CHX. Such compounds are referred as vinylic halide. Vinylic halide. If we look at this particular halide, whether it will give SN1 or not, let's see. As soon as this X is departed, we'll have the formation of vinyl carbocation, and vinyl carbocations are least stable carbocation, so will not no SN1. No SN1. Am I clear? Similarly, this one. This one will also not give SN1 reaction. Why? The reason is, as soon as the halogen is departed, in the first step, we'll have the formation of phenyl carbocation, and phenyl carbocation formed is a highly unstable carbocation. Cannot be formed. Highly unstable. So it will also not give SN1 reaction. So if you see such halides, don't do SN1 reaction in such halides. Am I clear, students? Okay, few more examples. This one, CH2X. Yes, it will definitely give SN1 reaction, and even at a faster rate. Why? Because as soon as this halogen is departed, I will have my carbocation, that is benzylic carbocations, PHCH2 positive, highly stable carbocation, right? So will definitely give SN1. More alkyl halide. This one, CH2 doubly bonded CH2X. Although it looks as like a primary alkyl halide, but after the departure of this halogen, I will have the formation of CH2CH2 positive, right? Allylic carbocation, resonance stabilized carbocation will definitely give SN1 reaction. So if you see allylic halide, benzylic halide, 3-degree alkyl halide, there you can readily do SN1 reaction. If you see vinylic halide, phenyl halide or aryl halides, bridgehead alkyl halides, 1-degree alkyl halides, in those cases or in such alkyl halide, don't do SN1 reaction. Am I clear, student? Let's move ahead. The second factor which affects the rate of SN1 is solvent. Student, since this SN1 reaction is initiated by a solvent, so the role of solvent is really important. Greater is the ionization ability of solvent, faster will be the rate of SN1 reaction. In general, SN1 reaction is promoted by a polar, I'm talking in general, polar protic solvent. More is the ionization of solvent, better is the rate of SN1 reaction. So a solvent with higher dielectric constant will give SN1 reaction at a faster rate. Water having highest dielectric constant, it's giving at a much faster rate as compared to these solvents. Am I clear? So a solvent with high dielectric constant will give SN1 at a faster rate. Effect of leaving ability. The first step itself is the ionization. better is the leaving ability of this halide ion, faster will be the rate of SN1 reaction. So among halide ion we have I minus, Br minus, Cl minus, F minus. I minus is having a better leaving ability. So Ri, if R is same, then the rate of reaction, SN1 reaction will be much faster in alkyl iodide, then alkyl bromide, then alkyl chloride, and then alkyl fluoride, least in this particular case. Am I clear, students? Mainly SN1 reaction occurs in these alkyl halides. Am I clear? Okay, let's move ahead. Effect of attacking nucleophile. Student, the role of nucleophile is involved in second step, right? Which is a faster step. So nucleophile does not have any role in SN1 reaction. It does not impact or it does not affect the rate of SN1 reaction. In general, a poor or moderate type of nucleophile promotes SN1 reaction. SN1 reaction. A poor or a moderate type of nucleophile will favor SN1 reaction. Am I clear, students? Okay. Students, now let's discuss the next type of nucleophilic substitution reaction, that is SN2 reaction. Let's see how does this reaction occur. SN2, the name itself says nucleophilic substitution bimolecular. SN stands for nucleophilic substitution, 2 stands for bimolecular reaction. Students, basically in such type of reaction, the attack of nucleophile and the departure of halide ion occurs at a same rate. Am I clear? Let's try to understand. I'm having my alkyl halide Rx. It's treated with a nucleophile Nu minus. Here we don't have the formation of intermediate. Reaction occurs in a single step only. So see what happens. Basically in TS, this nucleophile is approaching the alkyl halide. As this nucleophile is forming bond with the alkyl part, the halide ion is getting departed in the form of X minus. Am I clear? This is my TS. And now finally, I am going to get my product as NUR. This is a single step reaction. Am I clear, student? SN2 reaction does not involve any intermediate. In SN2 reaction, we won't have the formation of carbocation. The departure of leaving group and the attack of nucleophile occurs at same rate. Am I clear? So we have only transition state. Let's discuss the mechanism of this particular reaction. Students, now let's focus on the mechanism of this SN2 reaction. How does this reaction occur? Unlike SN1 reaction, it is a one-step reaction. SN1 two-step reaction, SN2 one-step reaction. So if it's a one-step reaction, we won't have the formation of intermediate, no intermediate. Right? So no carbocation formation, no carbon ion formation here. Am I clear, student? Okay. Now let's discuss the mechanism. I'm having my nucleophile Nu minus and it is treated with a substrate methyl halide CH3X. Student, here the nucleophile approaches from the backside. It approaches from the backside. You may say, what's the reason behind it? Student, we can easily understand it like this. Basically, this halogen will get departed in the form of halide ion, right? And this halide ion will have anionic character. Nucleophile is also having an anionic character. If it approaches from the front side, can I say it will encounter inter-electronic repulsion. In order to avoid that, the nucleophile approaches from backside. This is one of the reasons through which we can explain why nucleophile is approaching from backside. There is one more reason, and that we can understand through molecular orbital theory. Student, CX. This particular bond is referred as bonding molecular orbital, BMO. Exactly at 180 degree, we have a ABMO. And in alkyl halide, this ABMO is vacant, right? So nucleophile can approach to this ABMO, and this ABMO is exactly at 180 degree. That's why the nucleophile is approaching from backside. This is the second reason through which we can explain why nucleophile is approaching from backside. Now, as soon as this nucleophile approaches to this electrophilic center, halogen gets departed in the form of halide ion, and both this process occurs simultaneously. As this NuC bond is getting formed, this CX bond is getting cleaved. Am I clear? So we'll have our transition state, and the transition state is like this: C H H H X having del negative, Nu having del negative. This is our TS, transition state. Student, basically this transition state is penta-coordinated. But if someone asks you what is the hybridization, what will you say? It's still sp2 hybridized. The TS here is sp2 hybridized because these two bonds are partial bonds. So we have only three bonds, CHHH. Am I clear? This Nu and X bonds are the partial one. One more thing. This TS is having a anionic character. Anionic character. So if any electron withdrawing group is attached to the carbon, can I say the stability of this TS will increase? To an anionic species, if the electron withdrawing group is attached, the stability increases. Am I clear? And if stability of this TS will increase, obviously the rate of reaction will increase. So in SN2 reaction, if electron withdrawing group is attached, rate of reaction will increase. In SN1 reaction, if electron donating group is attached, then rate of reaction will increase, because there the electron donating group will stabilize the carbocation, whereas in case of SN2 reaction, the TS is having anionic character, and here the electron withdrawing group will stabilize the TS. Higher is the stability of TS, faster is the rate of reaction. And finally, my product will be like this: NuCH3 plus X minus. So student, here if I talk about the stereochemistry of this SN2 reaction, we will have complete inversion. Complete inversion, and this inversion is referred as Walden inversion. Am I clear? Let's move ahead. Nucleophile attacks on the substrate from just opposite side to the leaving group. We have discussed about this, right? Okay, so we have a complete inverted product. Second one, hybridization of the carbon, alkyl halides, or the hybridization of cation at which the substitution occurs changes from sp3 to sp2. Initially, alkyl halide was sp3 hybridized. The carbon there was sp3 hybridized, and in TS, the carbon is sp2 hybridized. We have discussed about this point also. It's a bimolecular reaction, one-step concerted process. Reaction occurs through transition state. Students, since it's a single step reaction, and in first step both nucleophile as well as alkyl halide is involved, can I say the rate of reaction will depend on alkyl halide as well as nucleophile. Higher this concentration of alkyl halide, higher the concentration of nucleophile, better will be the rate of SN2 reaction. Am I clear? One more thing, since nucleophile is involved in the rate determining step, since nucleophile is involved in rate law expression, can I say a stronger nucleophile will promote SN2 reaction. A stronger nucleophile will promote SN2 reaction, whereas a poor to moderate nucleophile will promote SN1 reaction. In SN2 reaction, nucleophile is involved in rate law expression. Am I clear? Let's move ahead. This is the energetics of SN2 reaction. I'm having my substrate. This is a TS. TS is having a anionic character. Anionic character. One more thing. Lesser the bulkiness of this one, faster will be the approach of nucleophile, faster will be the rate of SN2 reaction. Am I clear, student? So if the alkyl halide is bulky, if R is bulky, the rate of SN2 reaction will be less. If R is sterically less hindered, then the nucleophile will approach at a faster rate. The rate of reaction will be very high. Am I clear? We'll talk about that. We have discussed about this also. Nucleophile is approaching from backside, so we will have complete inverted product. Inverted product. Here we won't get racemic mixture. We will have only one product, and that product will be a inverted one. Am I clear? Let's move ahead. Factors affecting the rate of SN2 reaction. Student, if I talk about the effect of substrate, already we have discussed. Nucleophile role is involved in the first step, right? And nucleophile prefers to attack on less hindered carbon, less hindered electrophilic center. Am I clear? So can I say a less hindered alkyl halide, sterically less crowded alkyl halide will promote SN2 reaction at a faster rate. Methyl halides will give SN2 at a faster rate. Then we will have 1 degree, then we'll have 2 degree. In 3 degree, SN2 will not occur. Am I clear? Students, SN2 reactions are very sensitive to steric crowding. So if there is alkyl chain present at alpha carbon or beta carbon, then the rate of SN2 will be very less. SN2 is more in less hindered carbon or less hindered alkyl halide. Therefore, the rate of SN2 reaction in case of alkyl halide follows this particular order. Methyl halide, then 1 degree, then 2 degree. In 3 degree alkyl halide, since it's sterically crowded, sterically hindered, the rate of SN2 reaction will be very less. I hope this particular concept is crystal clear to you all. Let's move ahead. Student, this is the relative rate at which SN2 occurs in different substrate. If the substrate is methyl, it's much more faster. If substrate is 3 degree alkyl halide, SN2 reaction does not occur at all. Even in case of neopentyl alkyl halide, here this alkyl halide is a 1 degree alkyl halide, but there is steric crowding at beta carbon. If there is steric crowding at beta carbon or even gamma carbon, SN2 reaction will not occur. Am I clear? Let's move ahead. If there is unsaturation at beta carbon, then in that case, resonance will occur. Why? Because the TS is sp2 hybridized, right? The alpha carbon in that transition state is sp2 hybridized. And if the beta carbon is also sp2 hybridized, then resonance will occur. And if resonance will occur, stability of TS will increase, the activation energy barrier will be less, and the rate of SN2 reaction will increase. So presence of unsaturation on beta carbon increases rate of SN2 reaction. The reason is stability of TS. Stability of TS. Higher the stability of TS, faster will be the rate of SN2 reaction. The best examples are allylic halides, CH2CH, CH2X. There is unsaturation on beta carbon. This carbon is the beta carbon. and it's sp2 hybridized. In TS, this particular carbon is also sp2, so resonance will occur, and because of resonance, this allylic halide will give SN2 reaction at a much faster rate. Similarly, in benzylic halide also, PH CH2X, here also SN2 will occur at a much faster rate. Am I clear, students? So SN2 reaction, just like SN1, will also occur here, and here also SN2 will occur at a faster rate. Let's move ahead. If I talk about other alkyl halides, just like SN1, in such halides, that is vinylic halide, CH2 doubly bonded CHX, here also SN2 reaction does not occur. In case of this one, aryl halide, SN2 does not occur. In case of bridgehead carbon, because of steric crowding, SN2 does not occur. Just like SN1, in these three alkyl halides, SN2 reaction also does not occur. Am I clear? Let's move ahead. Student, if I talk about the other factors which affects SN2, it's nucleophile. A stronger nucleophile will always promote SN2 reaction. In general, anionic nucleophile promotes SN2 reaction. If I talk about the effect of solvent, in general, polar aprotic solvent favors SN2 reaction. SN2 reaction. Am I clear? So, stronger nucleophile, polar aprotic solvent, and less sterically hindered alkyl halide will promote SN2 reaction. Am I clear, student? Now it's time to discuss the second most important chemical reactions of alkyl halide, and this particular reaction is referred as elimination reaction. If I talk about alkyl halide elimination, mainly we have two types of elimination. One is dehydrohalogenation, where the removal of one hydrogen and one halogen occurs to form alkene. One more important reaction is there in case of elimination of alkyl halide, and that is dehalogenation. It is mainly observed in case of vicinal dihalides. Here we remove both the halogens to form alkene. But before discussing dehydrohalogenation and dehalogenation, let's first of all discuss in general the detailed mechanism of elimination reaction. Student, if I talk about this elimination reaction, it's mainly carried out, or it's mainly initiated by a base. What is the function of base? To snatch acidic hydrogen. So this base will snatch the acidic hydrogen. As soon as the acidic hydrogen is snatched, one of the leaving group gets departed. So in elimination reaction, in general, I will have the removal of one acidic hydrogen and the leaving group. If both hydrogen and the leaving group gets departed from the same carbon, it is referred as alpha elimination or 1-1 elimination. And alpha elimination always leads to the formation of carbene. We can see here the removal of X as well as Y is occurring from the same carbon, right? And it is giving me the formation of carbene. So alpha elimination always leads to the formation of carbene. We can consider one more example, CH, Cl, H, HCl. Let's take it. Now it's treated with a base OH minus. What this base will do? It will snatch the acidic hydrogen, right? So what it is going to do? It is going to snatch this hydrogen. As soon as this hydrogen is snatched, I will have C negative. This one, what it will do? This Cl minus will get departed, and I will have the formation of CH, Cl, and one unshared pair of electron, and it's nothing but carbene. Am I clear? So alpha elimination always leads to the formation of carbene. We have one more type of elimination, and that is beta elimination, where the base abstract the acidic hydrogen from beta carbon and the removal of leaving group occurs from alpha carbon. Am I clear? Removal of acidic hydrogen occurs from beta carbon and removal of leaving group occurs from alpha carbon, like this. One of the group from beta carbon, this carbon, let's suppose this is my reference carbon, so it's my alpha carbon. This is the leaving group. Carbon containing leaving group is referred as alpha carbon. The neighboring carbon of alpha carbon is referred as beta carbon. So it is going to be my beta carbon. Now, what the base is going to do? The base is going to snatch this group, right? Now, as soon as this group is snatched, the delocalization will occur and the departure of leaving group has to occur, and it will lead to the formation of alkene. So removal of beta hydrogen and removal of leaving group gives us beta elimination, which is also referred as 1,2 elimination. And student, this beta elimination is the most common elimination, and in this particular lecture mainly we will be talking about beta elimination only. Am I clear, student? Shall we move ahead? Let's move ahead. And now what's the function of this base? This base will approach on this beta carbon and it will snatch one of the acidic hydrogen. Now let's suppose the base is approaching this beta hydrogen at a rate R1 and the departure of this CX or the cleavage of the CX bond is taking at a rate R2. Now we may have different condition. We may have R1 equals to R2, means the attack of base on acidic hydrogen and the departure of leaving group occurring at same time, right? So in that case, elimination will occur in a single step. Elimination will occur in transition state itself. Such a reaction will be referred as E2 reaction. Am I clear? Where the departure of leaving group and the attack of base is occurring simultaneously. It's similar to SN2 type of reaction. Am I clear? We may have two more cases. Let's suppose R1 is greater than R2, means the rate of attack of base on acidic hydrogen is faster as compared to the departure of leaving group. Means base is first approaching this beta hydrogen and it's snatching it. Can I say in that particular case, first I will have the formation of carbon anion. Now this carbon anion will delocalize and the leaving group will get departed. Such a elimination will be referred as E1CB elimination, because here we are having the formation of a carbon anion, that is the conjugate base. E1CB, elimination conjugate base reaction. Am I clear, student? We may have one more case. R2 greater than R1 means first the departure of leaving group. If the departure of alkyl halide CX bond will take place, if this CX bond will cleave first, then I will have the formation of carbocation, and then the departure of this beta hydrogen is occurring. So first the carbocation is formed and then I am getting my alkene. In that case, the elimination is referred as E1 elimination. So R2 greater than R1, the reaction will occur via E1 pathway. R1 greater than R2, reaction will occur via E1CB pathway. And R1 equals to R2, the reaction will occur via E2 pathway. Am I clear? Student, we have one more elimination reaction, and that is internal elimination, EI. Mainly it occurs in case of Cope elimination and pyrolysis of ester, or such elimination is mainly a syn elimination, but we don't need to discuss this EI reaction because it's not there in your JEE mains as well as NEET syllabus. Am I clear? Let's discuss these three important elimination reactions, E1, E2 and E1CB one by one. Students, now let's discuss E2 reaction, that is elimination reaction by molecular reaction. If I talk about this particular reaction, in such reaction, first of all, it's a beta elimination. right? And in this beta elimination, the attack of base and the departure of leaving group occurs simultaneously. So this particular reaction will occur in one step. Am I clear? No formation of carbocation, no formation of carbanion. Am I clear, students? Such reactions are similar to SN2 type of reaction. The reactions occurs via the formation of transition state itself. No intermediate involved. Now let's discuss one example of this E2 reaction, and then we'll discuss the detailed mechanism of E2 reaction. Okay. Student, the best example of E2 reaction is dehydrohalogenation reaction. Whenever alkyl halide is treated with a strong base like alcoholic KOH, NaNH2 and terbutoxide, alkyl halide treated with a strong base like alcoholic KOH, NaNH2 or terbutoxide, in that case this alkyl halide will undergo beta elimination and the nature of reaction is going to be E2, and I will have the formation of alkene. CH3 H H H C H H Cl. Alcoholic KOH is nothing but ethoxide ion, ETO minus K plus, and this one is a strong base. What this base will do? It will snatch one of the beta hydrogen. So what it will do? It will attack on this beta hydrogen. Simultaneously, as soon as the base attacks on this beta hydrogen, the departure of leaving group will occur, and I will have the formation of C H H doubly bond H H H. Removal of one hydrogen and one halogen is nothing but dehydrohalogenation. Am I clear, student? So in dehydrohalogenation of alkyl halide, we will have the formation of alkene. Is this clear? Shall we move ahead? Let's move ahead. Student, now let's discuss the mechanism of this E2 reaction. Okay. C, 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 C. Okay. And this one's, let's suppose here also I am having one C. Let's suppose this particular carbon is containing halogen, and now it's treated with a strong base AlKOH, alcoholic KOH. Student, what is the function of base? The function of base is to snatch beta hydrogen. My base here is ETO minus. What this ETO minus will do? It will snatch the acidic hydrogen from beta carbon. Which carbon is the beta carbon here? Can you tell me? Student, can I say this particular carbon is your alpha carbon? The neighboring carbon of alpha carbon is referred as beta carbon. So this one is my beta carbon, and this is also my beta carbon. This is beta 1 carbon, beta 2 carbon. Now we have to check whether which one is containing hydrogen. This one also containing hydrogen, CH3, and here also this carbon is also containing one hydrogen. Now from where I am going to remove hydrogen? From which beta carbon I am going to remove hydrogen? On which beta carbon the base will attack? In E2 reaction, the base will always prefer to snatch beta carbon from more, or beta hydrogen from more substituted carbon. Let me write that. In E2 reaction, if we have two or more different types of beta carbon or beta hydrogen, they always remove beta hydrogen from the carbon which is more substituted. Am I clear? And If I am going to remove beta hydrogen from a more substituted carbon, the product formed will be referred as ZF product. If I am going to remove beta hydrogen from less substituted carbon, in that case I am going to get Hofmann product. So if I remove hydrogen from beta 1 carbon, in that case I will get Hofmann product. If I am going to remove hydrogen from beta 2 carbon, I am going to get ZF alkene. ZF alkene. Am I clear, students? In general, if the base is not that bulky, always form ZF alkene. Am I clear? Okay, so this alcoholic KOH is going to snatch hydrogen from beta 2 carbon. Simultaneously, as soon as the base attacks on beta 2 carbon, the departure of leaving group will occur. And first I will have the TS like this. C, C, C. Now this H bond is cleaving. It is getting attacked by the base. ETO minus is approaching. And here I will have C, and then the departure of leaving group X in the form of X minus, and then CH3. Simultaneously I will have the formation of a pi bond. As soon as this one gets removed, I will have the delocalization and the departure of leaving group, right? So this is the TS, and now this TS is basically having a character like alkene. Now if I look at this particular transition state, it's having a character, or the structure looks similar to that of alkene. And if I talk about alkene, the stability of alkene in general is dependent on alpha hydrogen. More is the number of alpha hydrogen, more is the stability of alkene. We have studied hyperconjugation. Stability of alkene, if resonance is not there, is dependent on hyperconjugation. More the number of alpha hydrogen, more is the substituted alkene, more is the stability. Am I clear? Now the final product, you remove this beta hydrogen, you remove this halogen and this hydrogen and form alkene. So the product is C, 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 doubly bonded C and C. This is my final product. Am I clear? So this reaction is occurring via single step, one step reaction, no intermediate. The reaction occurs via TS itself, and TS structure is similar to that of alkene. Partial double bond character. Am I clear? Okay, let's move ahead. Student, this is a single step reaction, right? Student, if it's a single step reaction, the first step is itself the RDS, and in RDS both alkyl halide as well as base is involved. So can I say the rate of reaction is dependent on the concentration of alkyl halide as well as it's dependent on the base? Am I clear? First order with respect to alkyl halide, first order with respect to base. So what's the overall order of this reaction? 2. It's a second order and bimolecular reaction. Am I clear? It follows concerted mechanism. The reaction occurs via TS itself. No intermediate. No intermediate. I hope this statement is also clear. Rate of reaction is directly proportional to the concentration of alkyl halide as well as the concentration of base. Student, in E2 reaction or E2 reaction is dependent on the nature of base. Stronger the base, better will be the E2 reaction. Am I clear? In general, E2 reaction is carried out by stronger base itself. We have 3 types of base which will in general will promote E2 reaction: alcoholic KOH, NaNH2 or terbutoxide ion, RO minus. Am I clear? Okay. So rearrangement is not possible here. Why rearrangement is not feasible? Because we don't get intermediate. The carbocation is not formed. The reaction is occurring in a single step, TS itself, and in TS we don't have any rearrangement. Am I clear? Now, student, this stereochemistry of E2 reaction is really important. For E2 reaction to occur, the beta hydrogen and the leaving group should be anti-periplanar. What do we mean by this statement anti-periplanar? Means the carbon containing the leaving group and the beta hydrogen should be at anti-position with respect to each other. If one of them is at wedge, the other one has to be on dash. Suppose here if the halogen is on wedge, means here hydrogen has to be on dash. Then only I will do E2 elimination. For E2 elimination, both beta hydrogen and the leaving group should be anti-periplanar. They should be at anti-position with respect to each other. Student, if I talk about the factors affecting E2 reaction, it's dependent on alkyl halide. So can I say in general, more is the substituted alkyl halide, better will be the stability of TS, because TS is having a partial alkene character whose stability depends on the number of alpha hydrogen. So can I say students in general will have a faster E2 reaction in case of 3-degree alkyl halide, then 2-degree alkyl halide, and then primary alkyl halide. Students, at the same time, the rate of E2 reaction will also depend on the nature of leaving group. Better is the leaving ability of the leaving group, faster will be the rate of E2 reaction. Right? So E2 reaction will be observed much faster in case of alkyl iodide, then alkyl bromide, then alkyl chloride, and least in case of alkyl fluoride. Am I clear? Already have discussed about it. Setjeff product and Hoffman product. If I am removing beta hydrogen from a more substituted carbon, in that case I am going to get a more substituted alkene, and the product is referred as Setjeff alkene, like this one. Right? I am having this, and what I am going to do, this one is also my beta carbon and this is my beta carbon, but this beta carbon is a 2-degree beta carbon, more substituted one, and this one is a primary beta carbon, 1-degree beta carbon. So from where I should remove hydrogen? From more substituted beta carbon. So I'm going to form the product like this. Am I clear, student? Okay. Here also you can see this is my beta carbon and this one is also my beta carbon. It's 1-degree beta carbon. It's a 3-degree beta carbon. Am I clear? Which one is more substituted? This one. Do we have any acidic hydrogen here? Yes. This one is the acidic hydrogen. So this base will snatch beta hydrogen from beta 2 carbon rather than beta 1 carbon. And I'm going to write the product like this. CH3 CH doubly bonded CH CH3 CH3, or this H is removed, right? Okay, so this is my final product, and this product is referred as Setjeff product. Removal of beta hydrogen from more substituted carbon always gives us a more stable alkene, and the alkene formed is referred as Setjeff alkene. Am I clear? Let's move ahead. Student, in case of E2 reaction, if the leaving group is poor or if the base is bulky, then the bulky base finds difficulty to approach to a more substituted carbon. In that case, the base will approach to a less substituted carbon. It will snatch acidic hydrogen from a less substituted carbon, and in that case I am going to get Hoffman alkene, the less substituted product. Am I clear? Like this one. If I am having a base like this, terbutoxide ion, diisopropylamine, triethylamine, all these bases will always lead to the formation of Hoffman alkene. Am I clear? If the base is bulky, if it's a stronger base, but if it's a bulky, then always form Hoffman alkene. Always remove beta hydrogen from the carbon which is less substituted. Am I clear, student? Let's move ahead. like this one. See, student, if we look at this particular example, I'm having terbutoxide ion. The base is bulky. If the base is bulky, then what you are going to do? You are going to remove hydrogen from a beta carbon which is less substituted. Let's see here. This one is also my beta carbon, and this one is also my beta carbon. This beta carbon is 1 degree, whereas this one is 2 degree. Can I say 1 degree is less substituted? So if the base is bulky, I am going to remove beta hydrogen from less substituted beta carbon. So from 1 degree I am going to remove this hydrogen, and simultaneously this halogen will get removed, and I will have the formation of Hofmann alkene. CH3, CH2, C, CH3, doubly bonded CH2. Am I clear? Whereas in this particular case, the base is ethoxide ion. It's not bulky, right? Then I will always form ZF alkene here. And in ZF alkene, you remove hydrogen from a more substituted beta carbon. So here you are going to remove this hydrogen and this halogen. So the product formed will be CH3, CH, doubly bonded C, CH3, CH3. Am I clear, student? So the first one is the ZF alkene, second one is the Hofmann alkene. Moving ahead, the next type of elimination reaction that we have to study is there on the screen, and it's unimolecular elimination reaction. That's E1 reaction. If I talk about the mechanism of this particular reaction, it's similar to that of SN1 reaction. In this SN1 reaction, what was the first step? The first step was ionization of alkyl halide, right? And the formation of carbocation. Here also, in the first step, I will have the ionization of alkyl halide and the formation of carbocation. And student, whenever a carbocation is formed, it's always formed in a slow step. Am I clear? Now here in the second step, the base will attack on the beta carbon and it will snatch one of the beta hydrogen to form alkene. Am I clear? Let's discuss the mechanism. Let's suppose I'm having an alkyl halide like this. This one is my alkyl halide X. Okay. It's treated with a polar protic solvent, PPS. Can you tell me one polar protic solvent? Water. What this water will do? It will do the ionization of the substrate. So in the first step, I will have the formation of this particular carbocation. Am I clear? The ionization occurs in the TS first of all, and then I will have the formation of intermediate carbocation. If rearrangement is feasible, it may undergo rearrangement, but right now here I'm having a 2 degree carbocation, and further it won't undergo rearrangement. Am I clear? Now in the second step, that is step 2, the base will come into picture and the base will attack. It will snatch one of the beta hydrogen, right? And it will snatch one of the beta hydrogen from a more substituted carbon. Here also I should form a more stable alkene. Am I clear? So it is going to remove beta hydrogen from this particular carbon, and I will have the formation of C doubly bonded C, C. Right? So just like SN1 reaction, here also the reaction occurs in 2 steps. The first step, which is the rate determining step, involves the ionization of alkyl halide leading to the formation of carbocation. Carbocation once formed will undergo rearrangement to give us a more stable carbocation, and to this more stable carbocation the base will attack and it will snatch beta hydrogen from more substituted beta carbon. Am I clear, student? Let's move ahead. Student, since in RDS only alkyl halide is involved, so unlike E2 reaction, E1 reaction does not depend on concentration of base. At the same time, it does not involve or it does not depend on the nature of base. Student, in general, a poor to moderate type of base promotes E1 reaction. Am I clear? Whereas a stronger base will promote E2 reaction. Here, if I talk about the rate law of this reaction, rate is directly proportional to concentration of alkyl halide, just like SN1. More is the concentration of alkyl halide, faster will be the rate of reaction. At the same time, it also depends on the nature of substrate. Since the first step is the formation of carbocation, more is the stability of carbocation, more is the stability of TS, more is the stability of intermediate, lesser will be the activation energy barrier, faster will be the rate of reaction. Am I clear, student? So just like E2 reaction, here also a 3 degree will give a faster E1 as compared to 2 degree. In 1 degree, this E1 reaction is rarely observed, not observed, because 1 degree carbocation is unstable carbocation. Am I clear, student? Reaction intermediate is carbocation, so rearrangement is possible. Am I clear? Next one. In the second step, what happens? The removal of proton from beta carbon occurs, leading to the formation of more stable alkene. Shall I move ahead? Let's move ahead. Now, if I talk about the energetics of this particular reaction, it's almost similar to that of SN1 reaction. On y-axis, I'm having my potential energy, and x-axis, progress of reaction or reaction coordinates. Here, I'm having my alkyl halide Rx plus base B minus, right? The first step is the ionization, and I will have the formation of my intermediate, right? This intermediate may undergo rearrangement to give us a more stable carbocation. This is my more stable intermediate, right? And then finally, I will have my second TS. This is TS1, this is TS2 or TS3, because this intermediate is also undergoing rearrangement. Student, it is the most stable carbocation, the rearranged carbocation. It was the initial carbocation. Here the departure is occurring R X del negative, R del positive. Now here I am having my most stable carbocation. To the most stable carbocation, the base will attack on beta carbon and it will snatch the beta hydrogen. So here what will happen? I will have, let's suppose I'm having a carbocation like this. This one is my carbocation, so base is snatching this beta hydrogen B minus, and I'm having the formation of alkene, and finally here I will get alkene as my final product. Am I clear? This is how E1 reaction occurs. Let's move ahead. Solvolysis. Just like SN1, this particular reaction is initiated by a solvent, so we say it as solvolysis reaction. First step, ionization. So what will happen? We'll have the formation of CH3, CH2, C, CH3, CH3, positive. Is it the most stable carbocation? Definitely yes. Now I'm having two different beta carbon. This one also and this one also. I'm going to remove beta hydrogen from the carbon which is more substituted. This one is more substituted. So I'm going to remove one of the hydrogen from here, and the product is CH3 doubly bonded C, CH3, CH3. Now you may ask, sir, where we will do SN1 and where we will do E1. Student, in both the case, the nucleophile as well as the basic strength is not that strong, right? Poor to moderate nucleophile and poor to moderate base promotes SN1 and E1 reaction respectively. If temperature is not given, do SN1. If temperature is given, if this delta sign is given, heat is provided, heat, do elimination, E1 reaction. If heat is not given, do SN1 reaction. Am I clear? Okay. Student, in general, the most common example of E1 reaction is dehydration of alcohol. Alcohol, whenever treated with a protic acid like H2SO4, S3PO4, always promotes or always undergo elimination via E1 pathway. So whenever alcohol is treated with any protic acid like S3PO4, H2SO4 at higher temperature. At a temperature above 160 to 180 degrees centigrade, then we will have elimination reaction, and this alcohol will undergo dehydration to form a more stable alkene. Am I clear? If I talk about the reactivity, 3 degree alcohol will give a faster E1 as compared to 2 degree, and 2 degree will give a faster E1 reaction as compared to a primary one. Am I clear, student? Let's move ahead. If I talk about the mechanism, let me discuss one of the reaction of alcohol, dehydration reaction. OH. It's treated with H2SO4. H2SO4 at 180 degrees centigrade. Student, what this H2SO4 will do? It will protonate alcohol. H2SO4 acts as acid, and this acid is a source of H plus. This H plus will do the protonation. So first, in the first step, I will have the protonation. OH positive. This H2O positive is a very good leaving group, so I will have ionization. This ionization will give me a carbocation like this. Now, 5-member ring, and just outside this ring I am having a 1 degree carbocation. Will it undergo rearrangement? Yes. Whenever we have a 5-member ring, and if there is positive charge on carbon just outside the ring, the ring will undergo ring expansion, and here I will have ring expansion, which will give me a carbocation like this. We have done it in reaction mechanism chapter, this rearrangement reaction, right? And now from this carbocation I am going to snatch one beta hydrogen, and which will give me alkene like this. Am I clear? So this is how E1 reaction occurs, student. I hope this is also crystal clear to you all. Student, let's discuss the factors affecting the rate of E1 reaction. Student, if I talk about the substrate first of all, the first step in the E1 reaction is the ionization, and this ionization gives us a carbocation. More is the stability of carbocation, faster will be the rate of E1 reaction. Can I say a more substituted alkyl halide will give us a more stable carbocation? So can I say E1 reaction will occur at a faster rate in case of 3 degree alkyl halide, or in case of a resonance stabilized alkyl halide as compared to other alkyl halides? Am I clear? So students, E1 reaction will occur at a faster rate in 3 degree alkyl halide, 3 degree, then 2 degree. E1 reaction is rarely observed in primary alkyl halide. Am I clear? More is the stability of carbocation. Whenever you have to do E1 reaction, simply do the ionization, check the stability of carbocation. More is the stability of carbocation, faster will be the rate of E1 reaction. Am I clear? Shall I move ahead? Let's move ahead. E1 reaction. The first step does not involve any base. So E1 reaction, just like SN1 reaction, this E1 reaction is independent of concentration as well as nature of base. Am I clear, student? In general, a weak or a moderate type of base promotes E1 reaction. This E1 reaction is carried out at higher temperature in general. Am I clear? Okay. If I talk about the nature of solvent, a solvent with higher dielectric constant, with higher ionization constant will promote E1 reaction. Can you tell me the reason? Because the first step is the ionization step. The first step is initiated by a solvent itself. In general, a polar protic solvent will promote E1 reaction. Am I clear, student? Okay. Students, moving ahead, the next type of elimination reaction which we have to study is E1CB reaction, unimolecular conjugate base reaction, E1CB reaction. Student, here the base attacks on the beta hydrogen first. We will have the formation of carbanion, and now this carbanion on delocalization will lead to the departure of leaving group, and I will have the formation of alkene. So first in E1CB reaction, the first step is the formation of conjugate base, or first step is the formation of carbanion. Am I clear? Okay. So here, if E1CB reaction has to occur, the beta hydrogen has to be more acidic. Then only the base will easily snatch this acidic hydrogen at a faster rate. Am I clear, student? Basically, it's also a two-step process. Two-step process. The first step, step one. Step one. Attack of base on beta hydrogen and formation of carbanion. Am I clear? Formation of carbanion. Now in the second step, step 2, departure of leaving group will take place. Departure of leaving group will take place. If E1CB reaction has to occur, the beta hydrogen has to be more acidic. Now student, if I am having more than 2 beta hydrogen, if we are having more than 2 different types of beta carbon, from which beta carbon you are going to snatch hydrogen? Here we are having the formation of carbanion. Lesser is the substitution of carbanion, more is the stability, right? A 1 degree carbanion is more stable as compared to 2 degree carbanion. 2 degree carbanion is more stable as compared to a 3 degree carbanion, right? So if you are having an acidic hydrogen, if you are having a stronger base, you are going to do E1CB reaction, and in this E1CB reaction, you are going to snatch beta hydrogen from that carbon which is less substituted. Am I clear? You are going to remove most acidic beta hydrogen. Am I clear? Simply remove the acidic hydrogen, check the stability of carbanion, and then do elimination reaction. Am I clear, student? Okay. Substrate must be containing acidic hydrogen, and for E1CB reaction, these are the two most important conditions. Leaving group should be poor, and the beta hydrogen has to be more acidic. The base in general should be stronger. Base has to be stronger, leaving group should be poor, and the beta hydrogen has to be more acidic. Am I clear? Or we can say presence of electron withdrawing group should be there on beta carbon. If electron withdrawing group is there on beta carbon, it will make the beta hydrogen more acidic, right? And if beta hydrogen is more acidic, base will easily snatch it, and I will have the formation of carbanion. We can see here in this particular example, I am having PH S double bond O S double bond O CH2 O PH, right? Okay, student, this is my leaving group. This one is my leaving group, right? Leaving group. Now, and this particular carbon is my alpha carbon. So this is my beta carbon. Now I will check whether the beta carbon is acidic or not. Yes, it's highly acidic because the electron withdrawing group is connected here. EWG is connected here, right? And now this EWG will stabilize the carbanion. And if carbanion is stable, means the compound is acidic, right? If conjugate is stable, means the parent compound is having acidic behavior. Now the base will snatch this beta hydrogen. I will have the formation of carbanion in the first step, and now this carbanion will delocalize. As soon as it delocalizes, it leads to the formation of alkene. The first step is the attack of base leading to the formation of carbanion. Second step is the departure of leaving group. Am I clear? We have one more example. The leaving group is poor here. Poor leaving group. Fluoride ion is a very poor leaving group. Now this Beta hydrogen is slightly acidic because of the presence of electron withdrawing group minus I group. It's making beta hydrogen relatively more acidic. Now the base is attacking here. It's leading to the formation of carbon ion. This carbon ion is delocalizing and is giving us alkene. Am I clear, students? So this is how even CB reaction occur. When this even CB reaction is occurring, the base should be stronger, beta hydrogen should be acidic, and the leaving group should be poor. These three are the mandatory conditions for a reactions to occur via even CB pathway. Let's move ahead. So this is how substitution reaction and elimination reaction occurs in case of alkyl halide. We have discussed all the different mechanisms involved in case of nucleophilic substitution reaction also, and in case of elimination reaction also. Student, now let's briefly discuss few more reactions related to this alkyl halide. The first one, reaction of alkyl halides. Reaction of alkyl halide of alkyl halide with LiAlH4. LiAlH4. What is this LiAlH4? Lithium aluminohydride. LiAlH4 is an excellent source of H-. This H- can act as like a nucleophile as well as it can act like a base, right? Now, if this LiLH4 is treated with 1 degree alkyl halide, in that case, I will have the formation of alkane. If it's treated with a 2 degree alkyl halide, then also this H- will have a nucleophilic behavior. It will attack on alkyl halide via SN2 pathway, and I will have the formation of alkane only. But if the alkyl halide is 3 degree alkyl halide, and now if it's treated with LiAlH4, in that case, this H- will act as a base and it will do elimination reaction, and I will have the formation of alkene. Am I clear? The first two reactions are the example of substitution reaction occurring via SN2 pathway. The third one is elimination reaction occurring via E2 pathway. Am I clear, student? Okay. If I talk about few more reactions of this alkyl halide, one of the most important reaction is Williamson synthesis of ether that we have studied in the chapter alcohol phenol ether, right? Still, let's do a quick revision related to this Williamson synthesis of ether. Here what happens, first of all, we take alcohol. This alcohol is treated with a strong base NaOH. I will have the formation of alkoxide ion because acid base reaction will occur, RO minus Na plus, right? Now this alkoxide ion may act like a base, as well as nucleophile. If this alkoxide ion is treated with 1 degree or 2 degree alkyl halide, then it will have the nucleophilic behavior. It will have a nucleophilic behavior. It will attack from backside via SN2 pathway, and this halogen will get departed. I will have the formation of ROR dash ether. But if R dash X is 3 degree alkyl halide, in that case, this RO minus will act as a base, and what it will do? It will do elimination reaction. Elimination reaction will occur, and if elimination reaction will occur, I will have the formation of alkene. Am I clear, student? I hope these things are crystal clear to you all. Okay, student, we have one more important reaction related to this alkyl halide, and that is free radical substitution reaction of alkyl halide. We have studied this particular reaction, one of the most important reaction in case of hydrocarbon. When we were doing the alkene part, we have studied this particular reaction, Wurtz reaction. Student, whenever alkyl halide is treated with sodium in the presence of dry ether, first we'll have the formation of alkyl radical, which may undergo combination reaction, which may undergo dimerization reaction to give us higher alkane. Am I clear? Student, in this reaction, alkyl halide is treated with sodium metal in the presence of dry ether so that hydrocarbon alkene is obtained as a product. RCl treated with Na in the presence of De will have the formation of Ara. If I talk about the mechanism of this reaction, first sodium in the presence of polar aprotic solvent will undergo de-electronation, will undergo oxidation. Na will undergo oxidation, it will release one electron. Now, this RCl will undergo homolytic cleavage. As soon as it undergo homolytic cleavage, I will have the formation of carbocation. This electron will attack here and I will have the formation of R dot, alkyl radical. And whenever a radical is formed, it readily undergo combination reaction or dimerization reaction. This R dot will combine with one more R dot and will give us higher alkene. We have done all these reactions in the chapter hydrocarbon. If you have any doubt, please refer to that particular lecture. Am I clear? So basically, there are two mechanisms through which this reaction occurs. First one is free radical, already we have discussed. Even this Wurtz reaction also occurs via carbanion mechanism. What happens in that case? 2 moles of sodium gives us 2 moles of Na plus 2 moles of electron. Rx treated with 2 moles of electron will give us R minus. This R minus acts as a nucleophile, and what this nucleophile will do? It will do substitution reaction with one more mole of Rx. It will do SN2 reaction and I will have the formation of higher alkane. Am I clear, students? Students, through Wurtz reaction, we cannot synthesize methane. Am I clear? Students, so that's all about the chemical reactions of alkyl halide. If you want to practice questions related to the chemical reactions of alkyl halide, we had one Menti quiz session. It's there in the playlist itself. You can follow that particular lecture. We have solved at least 30 questions related to the chemical reactions and the chemical properties of alkyl halide. Student, now it's time to discuss aryl halide. Students, now it's time to discuss about haloarenes, or we say it as aryl halide. First of all, let us talk about the structure of aryl halide. Aryl halide. Student, if I look about the structure, I'm having benzene, right? On each carbon there is one hydrogen. In aryl halide, you need to simply replace one hydrogen with halogen. One of the hydrogen is replaced by halogen. On every other carbon we have hydrogen. This is the structure of aryl halide, or we say it as haloarenes. Can you tell me the hybridization of each carbon and halogen here? Student, if I talk about the hybridization of each carbon, each and every carbon in the ring is sp2 hybridized. All carbon atoms, all C atoms in the ring is sp2 hybridized. Am I clear? Am I clear, students? Tell me. Yeah. Now, can you talk about the hybridization of halogen? Student, although we have 3 lone pair and 1 bond pair, 1 sigma bond, 3 lone pair, still the hybridization is sp2. Why? Because one of the lone pair is used in resonance. This lone pair is used in resonance, right? So if it is used in resonance, it will act as a pi electron component and want to be counted in hybridization. Am I clear, students? So if I talk about the hybridization of this halogen also, this one is also sp2 hybridized. Student, so now what will happen? I'm having benzene ring and it is substituted with one halogen having lone pair. Will resonance occur here? Definitely yes. Definitely yes. So student, if I talk about the hybrid structure of haloarenes, it's having a structure like this. I'm having one halogen here. This halogen has donated its lone pair. So on this halogen, I will have slight delta positive. Now I will have a partial double bond character. And throughout the ring, every carbon atom will share one double bond. Right? Student, since the lone pair is delocalized into the ring, the ortho position and the para positions will be electron rich. So I am going to put one del negative here, one del negative here, and one del negative here. Am I clear? So this is the real structure, or we can say the hybrid structure of haloarenes or aryl halide. Students, if I talk about the substitution reactions, will haloarenes undergo substitution? Will it undergo SN1? No. Why? Why it won't undergo SN1? Because in SN1 we have the formation of carbocation after the departure of halogen. After the departure of leaving group, we have the formation of carbocation. If I remove halogen from here, I will have phenyl carbocation. And this phenyl carbocation is highly unstable, so it won't undergo SN1 reaction. Will it undergo SN2 reaction? The answer is again no. Why? Student, since here I am having a partial double bond character, so bond order is more. If bond order is more, bond energy will be more, right? So I will need a larger amount of energy to cleave this bond. So haloarenes does not undergo SN1 as well as SN2 reaction. Am I clear, students? Now let's talk about the general method of preparation of haloarenes, or the methods through which we can synthesize haloarenes. Shall we start that? Let's start that. GMP of haloarenes. Students, it's simply prepared by, or one of the best method through which we can synthesize haloarene is electrophilic aromatic substitution reaction, EAS. EAS, electrophilic aromatic substitution reaction, right? Student, let's see what is this electrophilic aromatic substitution. I'm having, and how do we synthesize haloarenes from here? I'm having a benzene ring. This benzene ring is treated with halogen X2 in the presence of Lewis acid. Lewis acid. Can you tell me a few Lewis acids? The Lewis acids can be AlCl3, BCl3, BF3, FeCl3, ZnCl2. All these compounds act as a Lewis acid because they have incomplete octet. Am I clear, students? Now, students, whenever this benzene is treated with halogen in the presence of a Lewis acid, the reaction is electrophilic aromatic substitution reaction. One of the hydrogen gets replaced by halogen and we will have the formation of halobenzene or aryl halide. Am I clear? Let's talk about the mechanism of this reaction. Students, I'm having halogen X bonded to X, right? Okay. Now it's treated with, first of all, Lewis acid, AlCl3. As soon as it is treated with a Lewis acids, can I say this halogen is having a lone pair? So this one will act as a Lewis base. AlCl3 will act as a Lewis acid. Now I will have acid base interaction, right? And in this acid base interaction, what will happen? This lone pair will be donated to the vacant p orbital of aluminium, and I will have the formation of X bonded to X. Since one of the halogen has donated its lone pair, so it is going to get a del positive, and this is bonded to AlCl3. Now it will get negative. Let's put it positive here directly. Now, positive charge on a highly electronegative element, is it stable? The answer is big no. Positive charge on relatively higher electronegative elements is highly unstable. So it will undergo cleavage. I will have heterolytic cleavage and it will cleave like this. So I will have the formation of X positive plus AlCl3 bonded to X negative. Now this X positive, positively charged species, will act as a electrophile. Students, now let's see how does this electrophilic aromatic substitution reaction occur. How does this X plus attacks on benzene ring? I'm having a benzene ring, right? This benzene acts as a nucleophile. We have studied about this, right, student? Why it acts as a nucleophile? Because it contains loosely held pi electron. As soon as this benzene is treated with halonium ion, one of the hydrogen is replaced by this halonium ion, and I will have the formation of aryl halide. Let's see the mechanism of this particular step also. Student, basically this reaction occurs in two steps. Step 1, aromaticity is lost. Basically this benzene is treated with halonium ion and the reaction occurs like this. One of the pi bond is cleaved, heterolytically cleaved. So I will have negative here, positive here. On negatively charged, this X plus will attack. So I will have the addition of this halonium here. I will have one hydrogen here. I will have the formation of carbocation here, pi bond here and pi bond here. This is step 1. Okay. Will it occur at a faster rate? The answer is big no. Aromaticity is lost. My reactant is aromatic, whereas my intermediate is non-aromatic. So this step is a very slow step. Very slow step. Student, now what will happen in step 2? Once again aromaticity will be regained. How? Let's see. Step 2. Basically now I am having a intermediate like this, positively charged H and X, and here I am having a pi bond and here also pi bond. Student, if I look at this particular hydrogen, it is somewhat acidic in nature because alpha hydrogen, and alpha hydrogen is always acidic in nature. We have studied it in hypoconjugation, right, student? So if it is acidic in nature, basically it will be removed in the form of H plus. We will have deprotonation, removal of hydrogen in the form of H plus, and I will have the formation of this aryl halide. So in step 2, aromaticity is regained. Step 1, aromaticity is lost. So can I say this step is going to be a fast step? Remove H plus. Am I clear? So students, whenever a benzene ring is treated with halogen in the presence of Lewis acid, we will have electrophilic aromatic substitution reaction, and finally the product is halobenzene. Students, this is how this particular electrophilic aromatic substitution reaction occurs. It occurs in two steps. Step 1, loss of aromaticity, addition of this halonium ion to benzene ring. Step 2, removal of this hydrogen in the form of H plus, or we can say deprotonation. Step 2 is a faster step. So rate determining step is step 1. Am I clear, student? More is the stability of this carbocation. Higher will be the rate of reaction. Student, one more important point related to this reaction. Sometimes you will see in the questions they will ask you kinetic and isotopic effects, right? In case of electrophilic aromatic substitution reaction. They will give you compare the rate C6H6, C6D6, C6D6. Students, in general, kinetic and isotopic effect is not observed in electrophilic aromatic substitution. You may say, why sir? Because basically we have the removal of this hydrogen in step 2, and step 2 is a faster step. Step 2 is occurring at a faster rate, and if it is occurring at a faster rate, can I say it won't impact the rate of reaction, right? But we have one exception. In case of iodination, this kinetic and isotopic effect is observed. Rest in all other case, whether it is fluorination, chlorination, bromination of benzene, in all such case, the rate of reaction in C6H6 will be same as that in C6D6, will be same as in case of C6D6. But in case of iodination, this kinetic and isotopic effect is observed. In that case, student, the rate of reaction in C6H6 will be more as compared to C6D6 as compared to C6D6. Am I clear, students? Students, I hope this particular method of preparation of benzene. Students, I hope this particular method of preparation of halobenzene is crystal clear to you all. Shall we move ahead to the next method? Let's move ahead. Student, the next method which we are going to discuss for the preparation of halobenzene is Sandmeyer reaction. Sandmeyer reaction mainly. Student, we have discussed about this. Let's quickly revise it. Student, in Sandmeyer reaction, whenever we have a diazonium salt, pH, N triple bond N, positive. If it's treated with a poor nucleophile Nu minus, what will happen? I will have nucleophilic substitution reaction. This N2 positive, being one of the best leaving group, will easily get departed, and I will have the formation of pH Nu. Am I clear? Plus N2. Am I clear, students? Now let's discuss how do we get this diazonium salt. Student, in order to prepare this diazonium salt, first we take nitrobenzene. This nitrobenzene is treated with metal in the presence of acid. Whenever we take metal in the presence of acid, it acts as a source of hydrogen. And what this hydrogen will do? It will do reduction reaction. It will do reduction reaction. Am I clear? So nitrobenzene will get converted to aniline, that is pH NH2. Now this aniline is treated with pH NH2 is treated with HNO2 at 0 to 5 degrees centigrade. This is nitrous acid. Am I clear, students? Aniline treated with HNO2 at 0 to 5 degrees centigrade, we will have the formation of pH N triple bond N positive, and it's nothing but benzene diazonium. Am I clear? Or diazonium salt. Now let's see how do we synthesize halobenzene from this diazonium salt. Student, here you can see a chain of reactions. So we can get different halobenzene. We can synthesize fluorobenzene, chlorobenzene, bromobenzene, iodobenzene from this diazonium salt. This is benzene diazonium chloride. How do we get it? Simply you take pH NH2, that is aniline, you treat it with NaNO2 plus HCl. You will have the formation of pH N triple bond N positive Cl negative, and it's nothing but benzene diazonium chloride. Now this benzene diazonium chloride is treated with a series of reagents, right? And then we get different products. If this benzene diazonium chloride is treated with Ki, we will have the formation of iodobenzene. If it's treated with CuCl, I will have the formation of chlorobenzene. If it's treated with CuBr, I will have the formation of bromobenzene. If it's treated with HBFO, this reaction is important. HBF4, I will have the formation of fluorobenzene. If it's treated with KNO2, I will have the formation of nitrobenzene. If diazonium chloride is treated with boiling water, I will have the formation of phenol. If it's treated with H3PO2, I will have the formation of benzene. Am I clear? So I hope this Sandmeyer reaction is crystal clear to you all. Shall we move ahead? Let's move ahead. Students, now it's time to discuss the chemical reactions of halobenzene. And if I talk about the chemical reactions of halobenzene, it mainly undergo two types of reaction. One, ESR, that is electrophilic substitution reaction, and the second one is nucleophilic substitution reaction. Let's see how does these reactions occur. Let's first of all talk about EAS, that is electrophilic aromatic substitution reaction of halobenzene. Student, if I look at the hybrid structure of this halobenzene, the structure is like this. X, double bond character and double bond character throughout the ring. Halogen has donated its lone pair, so I will have del positive over here and del negative over these three carbons at ortho and para positions. Now, ortho and para positions are electron rich position. So can I say all the incoming electrophile will get directed to ortho or para position? Am I clear? Student, if halobenzene is treated with any electrophile, this electrophile will either get substituted at ortho position or at para position. Now you may ask, sir, which one is major? Student, if I talk about this halobenzene, here I'm having halogen, and can I say this halogen, no doubt it's a plus M group. At the same time, it's a minus I group also. Am I clear? Now at ortho position, this minus I effect will be more dominating, right, as compared to the para one. So all the incoming electrophile will prefer to attack at para position. So student, if halobenzene is treated with electrophile, the para substituted one will be the major one and the ortho substituted will be minor one. Am I clear, students? Okay. Now let's talk about nucleophilic substitution reaction of halobenzene, NSR. Student, if I look at the structure of this halobenzene, because of the lone pair and because of the partial double bond character, this halobenzene won't easily undergo nucleophilic substitution, right? It will not undergo nucleophilic substitution reaction easily. Am I clear? Neither it will undergo SN1 nor it will undergo SN2. Basically, no doubt nucleophilic substitution reaction occurs here, but via different pathway, via different mechanism. Now it's time to discuss the different mechanism of nucleophilic substitution reaction of halobenzene or aryl halide. Discuss the nucleophilic substitution reaction of benzene. Okay, students, here I am having a halobenzene. Students, now let's discuss about the nucleophilic substitution reaction of halobenzene. Let's see how does this reaction occur. I'm having halobenzene. This halobenzene is treated with a nucleophile. This nucleophile will do substitution reaction. This halogen will get eliminated and I will have Nu getting substituted to this benzene plus X minus. Now, if I look at this reaction, basically it occurs via two different pathways. Depending on the nature of nucleophile, depending on the nature of substrate, we are having two different pathways through which nucleophilic substitution reaction of halobenzene will occur. The first pathway is referred as SNAE pathway and the second pathway is SNEA pathway. What does this A stand for? Nucleophilic substitution, addition, elimination. Here first the incoming nucleophile will get added, and then I will have the departure of this halogen. Am I clear? SNAE. Student, for this SNAE reaction to occur, presence of electron withdrawing group at ortho and para position is mandatory. At ortho and para position is mandatory. If I am having a halobenzene, and if at ortho and para position some minus I, strong minus I group is, or minus M group is present, then only reaction will occur via this pathway. Am I clear? SNAE pathway. How does this reaction occur? We'll see. Okay. The next one, SNEA, nucleophilic substitution, elimination, addition reaction. Here first we will have the departure of hydrogen. We will have the removal of hydrogen. Here I will have first acid base reaction. I will have the formation of an intermediate benzene, and on this highly unstable benzene intermediate, the incoming nucleophile will attack, and I will have my nucleophilic substitution reaction. Basically, this reaction pathway is also referred as benzene mechanism. Why benzene mechanism? Because we will have the formation of an intermediate which is referred as benzene. Students, if this nucleophilic substitution reaction has to occur via benzene mechanism, then this nucleophile should have highly basic character, and mainly this only nucleophile, NaNH2. If I am having halobenzene, and if halobenzene is treated with NaNH2, in that case, nucleophilic substitution reaction will occur via benzene mechanism, or will occur via SNEA pathway. I hope these two pathway conditions are crystal clear to you all. Now we are going to discuss the mechanism one by one. SNAE. I am having a halobenzene. This halobenzene is treated with a nucleophile. Student, at normal pressure and temperature, this reaction cannot occur, right? Because halobenzene, it's having a partial double bond character with the benzene, so it won't easily get departed. Am I clear? So student, what we do here, we substitute some electron withdrawing group, NO2 here, NO2 here. What this NO2 will do, we'll see. Okay. Student, basically what happens in the first step? In the first step, the aromaticity of the ring is lost. Okay, I'm having a benzene, here I'm having halogen, here let's suppose here I'm having a nitro group. Okay, in the first step, what I will do, I will cleave this double bond. So I will have this one, positive charge on this halogen, negative charge on this nitro group, right? And double bond, double bond. I hope this is crystal clear why this electron withdrawing group is mandatory. Basically, what this electron withdrawing group will stabilize the carbon ion. Am I clear? Student, in the next step, what will happen now? My incoming nucleophile, which is electron rich species, will attack on the electron deficient side, on this positively charged carbon, and I will have the formation, or I will have the addition of nucleophile, halogen nucleophile. Here I am having negative charge, nitro group, structure like this. This is my TS, or you can say intermediate. Now this negative charge is in conjugation with double bond, so can I say it will get delocalized, right? Okay, if it's getting delocalized, the negative charge will come over here. Further, it will get delocalized, negative charge will come over here, and finally the negative charge is here. In the next step, what will happen? This negative charge will delocalize here. As soon as it delocalizes here, this carbon will have 5 bonds, and carbon cannot make 5 bonds. So I will have the departure of this halogen as a leaving group, and finally I will have my product PHNU plus X minus this NO2. right? Okay, one more thing. Student, if I look at this particular intermediate, or you say TS, this TS is having a anionic character. Anionic character. Because two electron rich species are there. Am I clear? The presence of these two electron rich species make the TS anionic in nature, and that's why a electron withdrawing group will stabilize the TS, will increase the rate of reaction. Am I clear? So student, if I'm having halobenzene and if it's treated with a nucleophile and if it has to occur via SN-AE pathway, the presence of electron withdrawing group is mandatory. If there is no electron withdrawing group at ortho and para position, reaction won't occur. Am I clear? Now, let's have a look at the potential energy diagram of this reaction. Students, now let's have a look at potential energy versus progress of reaction. Okay, this particular diagram. Here is my substrate, that is aryl halide. Aryl halide treated with a nucleophile Nu minus. This is my TS. Basically, this TS is having a carbon ionic character, and finally, I am having my product pH Nu. Reaction is occurring via SN-AE pathway. If a reaction has to occur via SN-AE pathway, presence of electron withdrawing group, that is minus M group preferably, is mandatory at ortho/para position. Am I clear? More is the electron withdrawing group attached at ortho and para position, faster is the rate of reaction. Am I clear, student? Let's see. Let's suppose here I am having NO2, NO2, NO2 here. 3 electron withdrawing group here. Let's keep 2 electron withdrawing group here. Let's keep 1 electron withdrawing group here. Let's keep 1 electron withdrawing group here. No electron withdrawing group here. What do you say? In which case the rate of reaction will be fastest? More the electron withdrawing group, faster will be the rate of SN-AE in case of aryl halide. So can I say 3 electron withdrawing group? So this reaction will occur at a fastest rate than this one. Now if we look at these two reactions, minus I and minus M group. Minus I at para position is relatively weak. Minus I at ortho is relatively strong. Minus M is a distance independent effect, right? So can I say here, I will have the reaction at a faster rate. And this particular here, we won't have nucleophilic substitution reaction, right? Easily. Although it will also undergo nucleophilic substitution reaction, but under rigorous conditions. We will talk about that also. Student, if I talk about the different types of halides, in case of alkyl halide, the rate of reaction was in the order Ri, then Rbr, then RCl, then Rf. In case of aryl halide, the rate of reaction is ARF, then ARCl, then ARBr, then ARI. Can you tell me the reason why? Student, if I look at this mechanism, basically I am having positive charge here. Now, and this nucleophile will have a tendency to attack on this positive charge. More is the electron deficiency here. More is the electron deficiency on this carbon. Faster will be the attack of nucleophile. And more is the electronegativity of this halogen. Higher will be the electron deficiency. So can I say this F will make this particular carbon more electron deficient. So in case of aryl halides, the rate of nucleophilic substitution occurs like this. ARF, then ARCl, then ARBr, and least in case of ARI. Am I clear? Okay. Yeah. So under normal condition, if I am having an electron withdrawing group at ortho and para positions, at normal pressure and temperature, I will have my nucleophilic substitution. But if there is no electron withdrawing group, then the reaction won't occur under normal condition. Reaction will occur, but at very high pressure and very high temperature, right? Okay. We have to compare the rate of SN-AR reaction. We have just now discussed ARF, then ARCl, then ARBr, then ARI. Because here I am having a positive character, right? More is the electron deficiency on this particular carbon, faster will be the attack of nucleophile. Am I clear? Okay. Yeah. Now let's discuss the next type of nucleophilic substitution reaction of aryl halides. And this particular reaction occurs via SNEA pathway. First, elimination of acidic hydrogen and then addition of a stronger nucleophile. Okay, let's see how does this reaction occur. I'm having my aryl halide PHX. It's treated with a stronger nucleophile NaNH2. What will happen here? Here, students, simply this halide ion will get substituted by NH2 minus and I will have the formation of PHNH2. Although it's looking a very simple reaction, but it's not as simple as it's looking here. Let's discuss the mechanism of this reaction. I'm having my aryl halide, this one, right? This is my aryl halide. Students, on every carbon we have one hydrogen, and this hydrogen is connected to sp2 hybrid carbon everywhere. And if hydrogen is connected to sp2 hybrid carbon, obviously it is having somewhat acidic character. As soon as it is treated with a stronger nucleophile NH2 minus, this NH2 minus will also act as a stronger base, and what it will do, it will snatch the acidic hydrogen here. It will snatch this acidic hydrogen. As soon as it snatches this acidic hydrogen, I will have the formation of negative charge. Now what this negative charge will do? It will delocalize and will depart this halogen in the form of halide ion, and I will have the formation of a very unstable intermediate, and this particular intermediate is referred as benzene. Am I clear, student? This is my intermediate. After the removal of this acidic hydrogen, I'm having the formation of carbon ion here. This carbon ion is getting delocalized and halogen is getting departed in the form of halide ion, and we are having the formation of benzene intermediate. Benzene, right? Let's see the hybridization and the structure of this benzene. What's the hybridization here? sp2, 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 sp2. Now if we look at the structure of this benzene, some of you may say, so the two carbon like this, these two carbons are sp hybridized. No, still not sp hybridized. Basically this particular pi bond is formed by the overlap of two sp2 hybrid, two sp2 orbitals. Am I clear? Students, if we look at the structure of this benzene, some of you may say that two carbon in this benzene are sp hybridized. Let's see. The structure is like this. This is benzene. Now you may say, sir, these two carbons are sp hybridized. No, it's not sp hybridized. Basically, this particular pi bond is formed by the overlap of or lateral overlap of two sp2 orbital. Am I clear? So this particular carbon is not sp hybridized. Is this clear? Okay. Student, now this benzene is highly unstable. So this benzene will split like this. Here this particular pi bond will split like this. Positive, negative, right? Or we may have the structure like this. Negative, positive. Here, while cleaving this particular pi bond, you need to check the stability of carbanion and carbocation. Simply check the stability if any group is attached. Then check the stability of this carbanion and then accordingly form carbocation and carbanion. Am I clear? Now, on this carbocation, the nucleophilic part NH2 minus will attack, right? As soon as it attacks, see, now this NH2 minus will attack. Here I am having a negative charge, here I am having a negative charge. This NH2 minus will attack on the positively charged carbon. So if it's attacking here, I will have the formation of NH2 here. If the positive charge is here, then I will have the attack of NH2 minus here on this carbon, right? Here you need to check the stability. Am I clear, student? Now in the next step, simply the carbon ion, this particular carbon ion will get protonated by ammonia, and I will have the formation of PHNH2, aniline. Am I clear, students? So this is how the nucleophilic substitution reaction of aryl halide occurs via benzene mechanism. Although this particular mechanism is not that important for you all, this SNA pathway was more important. I hope you understood all these things. So student, with this particular lecture of alkyl and aryl halide comes to an end. Thank you all for watching this lecture. If you have any doubt related to this particular lecture, please do mention in the comment box. I will definitely reply to all your query. Once again, I thank you all for watching this lecture.